GCE Advanced Level Chemistry Practical Series, experiment number 37. Experimental determination of solubility product of calcium hydroxide. In this experiment, students, we aim to determine the solubility product of calcium hydroxide experimentally. Apart from that, we will be aiming to investigate the effects of common ions, temperature and pH on the solubility of calcium hydroxide. Now, we will be moving on to identifying the equipment and the chemicals we will be using for this experiment. Let's take a look at the chemicals and the equipment we will be using for this experiment. Now, in today's experiment, we are going to observe the solubility product or KSP of calcium hydroxide. So, we will be using calcium hydroxide solid for this experiment. Apart from that, we are going to determine the solubility of calcium hydroxide in different temperature conditions, in different pH, and when common ions are present in the medium. So, to carry out this experiment, we would need these 10 different solutions we have over here. We have 10 solutions over here, and we will be using all of these 10 different solutions to carry out today's experiment. So, using our nitric acid reagent bottle, we have prepared 3 different nitric acid solutions. We have over here 1 moles per decimeters cube concentrated nitric acid solution, and then we have formed 0.1 moles per decimeters cube concentrated nitric acid. We have 0.01 moles per decimeters cube concentrated nitric acid as well. So, all of these 3 nitric acid solutions were formed using our nitric acid that is present in this reagent bottle. Apart from that, we have sodium hydroxide. So, using sodium hydroxide solid pellets, we have prepared 2 sodium hydroxide solutions, one with 0.05 moles per decimeters cube concentration, the other with 0.025 moles per decimeters cube concentration. One 0.05 and the other 0.025 moles per decimeters cube concentrated. Apart from that, using calcium chloride solid, we have prepared 2 calcium chloride solutions as well. You can see over here, we have prepared a calcium chloride solution with 0.05 moles per decimeters cube concentration and 0.025 moles per decimeters cube concentrated calcium chloride solution is prepared. So, there are 2 calcium chloride solutions. See, these calcium chloride solutions are used to introduce the common ion calcium into the medium. Apart from that, we have 3 water containing beakers here. Right now, these beakers are not at these temperatures that are labeled. However, when we are carrying out this experiment, we will be taking each of these beakers and we will be subjecting them to the temperatures that are mentioned in the label. We have 3 beakers over here that contain water. Each of these beakers contain exactly 100 milliliters of distilled water, and you can see a temperature that is labeled in each of these beakers. So, right now the water in each of these beakers are not at those temperatures, but when we are conducting this experiment, we will first bring each of the beakers to those relevant temperatures, and then we will be carrying out our experiment. So, with the use of a water bath, the water in this beaker will be brought to a temperature of 50 degrees Celsius, and water in the beaker that I'm currently holding will be brought to a temperature of 90 degrees Celsius. One thing that you need to observe is that each of these beakers contain exactly 100 milliliters of solution or of water. So that observation is a must, students, because when it comes to this experiment, the very first step is to prepare calcium hydroxide saturated solutions using these solutions that we have over here, and we have to measure exactly 100 milliliters. So we have taken 100 milliliters of the solutions we have here and 100 milliliters of water into each of these beakers as well. So apart from these solutions, we will be needing HCl solution to titrate the calcium hydroxide that we have in the medium. So therefore, we will be using a hydrochloric acid stock bottle that we have over here, and we have prepared a 0.1 moles per decimeter cube concentrated HCl solution. So that solution will be used to titrate the hydroxide ions that are going to be found in the medium of calcium hydroxide solutions. Apart from these solutions, we'll be using thermometers, we'll be using pipettes with pipette filler. We have the pipette filler here, we have the pipette here. This is a 25 milliliter or 25 cubic centimeter pipette. We'll be using a stirrer, phenolphthalein indicator, titration flasks. Then we have a burette here. To carry out our titration, we will be using a burette along with a burette stand, a white color tie to see the color change very clearly, and we will be using a water bath setup as well. So what you see here is a water bath setup where there's a beaker and a tripod with a Bunsen burner. We have set up our water bath here. So we will be using a water bath as well. A water bath will mainly be used to bring the temperature of the water to different required temperature values. For example, when we are conducting this experiment, we need to bring the temperature of water to 50 degrees and 90 degrees respectively. So in order to do that, we will be using a water bath as well. So these are all of the equipment and the chemicals we will be using for this experiment. So now let's move on to the first part of our experiment. Students, let's take a look at what we will be doing in this practical and why we are carrying out the steps we are carrying out in this experiment. Calcium hydroxide is sparingly soluble in water, meaning calcium hydroxide is not very soluble in water, it is only slightly soluble in water. So when you dissolve calcium hydroxide in a volume of water, only a very small amount of calcium hydroxide will come into the aqueous medium as calcium 2 plus aqueous ions and hydroxide aqueous ions. If you add a very specific mass of calcium hydroxide and then observe how many calcium 2 plus ions and how many hydroxide ions are present in the medium, we can calculate calcium hydroxide's KSP, or in other words, calcium hydroxide's solubility product. So if you take a 100 milliliter volume of water and dissolve calcium hydroxide in it, you can produce a saturated solution of calcium hydroxide by dissolving around 1 gram of calcium hydroxide in 100 milliliters of water. And how are we going to be sure that we have produced a saturated solution of calcium hydroxide? If we have produced a saturated solution of calcium hydroxide, students, there will always be a small amount of solid that is not dissolved in that volume of water. So on the top layer, we will have calcium hydroxide solution, and at the bottom of the beaker, you would find some solid calcium hydroxide that is not going to be dissolved no matter how long you stir the solution. So at this point, we can be sure that we have produced a saturated solution of calcium hydroxide. And at this point, students, between the solid calcium hydroxide and the aqueous ions of calcium 2 plus and hydroxide in the medium, a special equilibrium will be established. This equilibrium consists of calcium hydroxide solid turning into calcium 2 plus ions and hydroxide 1 minus aqueous ions, and you have calcium 2 plus ions and hydroxide ions again joining together to form calcium hydroxide solid as well. So in this particular equilibrium, the forward reaction is not that favored, so the equilibrium position lies very close to calcium hydroxide solid, or in other words, equilibrium position lies very close to the left hand side of the equilibrium. So when it comes to determining the solubility product of calcium hydroxide, so solubility product of calcium hydroxide, or KSP, would be equal to the concentration of calcium 2 plus ions multiplied by the square of the concentration of hydroxide ions. So we need to find out both the calcium 2 plus ion concentration as well as the hydroxide ion concentration. And since there were no other species that were bringing calcium 2 plus ions into the medium, we can be very certain that calcium 2 plus ions only come into the medium when calcium hydroxide dissociates into forming Ca2 plus and hydroxide ions. So if you know that X number of moles of calcium hydroxide dissociated, we can be sure that X many moles of calcium 2 plus ions are in the medium and 2x many moles of hydroxide ions are in the medium. So if you can titrate and find out the hydroxide ions in the medium, half that number would be your calcium 2 plus ion number of moles. So through a titration, we are going to initially find out the hydroxide ion concentration, and then with that information, we will be able to figure out the calcium 2 plus ion concentration. This is in an aqueous medium without any other ions in it. So the example that I'm talking about is an example where we only have water. However, students, to carry out the titration, we can use the HCl solution that we showed earlier. 0.1 moles per decimeter cube concentrated HCl solution will be used to carry out this titration. And apart from that, students, solubility product of calcium hydroxide or any other solid for that matter will not change if the temperature remains a constant. However, when the temperature changes, the solubility product will also change. But the solubility of calcium hydroxide is going to be affected by both a common ion effect and pH, right? And when you change the temperature, since the KSP is changing, solubility of calcium hydroxide will also change. So solubility and solubility product are two different things. Solubility of calcium hydroxide is going to change based on pH, common ion effect, and temperature. However, the solubility product of calcium hydroxide will only change with temperature. So while keeping this information in mind, we can now move on to the very first step, where we will be taking all of these different solutions and we will be dissolving calcium hydroxide solid in each of these solutions. And we will be making sure only to use 100 milliliters of each of these solutions, and we are going to be dissolving roughly 1 gram of calcium hydroxide. Since calcium hydroxide is anyway going to be in excess when producing a saturated solution, we are not going to be overly concerned about measuring exactly 1 gram of calcium hydroxide. We can have roughly 1 gram of calcium hydroxide dissolved in each of these solutions, and at the end of forming each of these solutions or dissolving calcium hydroxide in each of these solutions, we should observe a small amount of calcium hydroxide solid at the bottom of each of these solutions. So to measure calcium hydroxide, we will be using this digital balance we have over here, and we will be measuring the calcium hydroxide onto this watch glass, and then we will transfer them into each of these beakers. We will stir each of the solutions really well with the use of a glass rod, and then we will allow each of these solutions to settle for a while so that they can establish an equilibrium over a period of time. So we will prepare these calcium hydroxide solutions, and after that we will allow these solutions to acquire an equilibrium. So we will allow them to settle for a period of time. In the case of different temperature water that we have over here, we will have to maintain the exact same temperatures that we have mentioned on the labels, and we will allow the calcium hydroxide solution to obtain an equilibrium over a period of time until calcium hydroxide and calcium 2 plus and hydroxide ions in the medium have established an equilibrium at that temperature. With that information, students, we can now move on to measuring the calcium hydroxide that we will be adding to each of these solutions. So before we move on to the solutions that we have prepared, it will be better if we can take water at 25 degrees Celsius and dissolve 1 gram of calcium hydroxide in 25 degrees Celsius to see what kind of solubility calcium hydroxide has when we dissolve 1 gram of calcium hydroxide in 100 milliliters of water that is at 25 degrees Celsius. So we will use a thermometer and let's measure the temperature of the water. The temperature of the water is at 25 degrees Celsius. Observe, the temperature of water is at 25 degrees Celsius. Now students, after ensuring that this water is at 25 degrees Celsius, we can now move on to measuring 1 gram of calcium hydroxide. We will place the watch glass on the pan of the digital balance, and then we will use the tare function to bring the reading to 0. After that, we will take our calcium hydroxide solid and we will add roughly 1 gram of calcium hydroxide into this water that is at 25 degrees Celsius. So students, we have measured 1.02 grams of calcium hydroxide. Let's transfer that into the water that we have over here. We are trying to prepare a saturated solution, meaning when you add 1 gram of calcium hydroxide, you will observe we have now added roughly about 1 gram of calcium hydroxide to this 100 milliliters of water. And we are trying to prepare a saturated solution of calcium hydroxide. So, when you are preparing a saturated solution of calcium hydroxide, once you stir this, you would notice that majority of calcium hydroxide over here is not going to be dissolved in water. You can see that is why you can see this cloudy nature in this aqueous medium, because majority of the calcium hydroxide solid particles are now suspended in this aqueous medium and are not dissolved in this aqueous medium. Only a small portion of the calcium hydroxide that we added is actually dissolved in this aqueous medium. So then we have two other water samples that we need to increase the temperature to 50 degrees Celsius and then to 90 degrees Celsius to see the solubility of calcium hydroxide. At those temperatures, we will not directly move on to those water samples now itself. However, we need to observe at 25 degrees Celsius, calcium hydroxide is not very soluble in just water. We can see majority of the calcium hydroxide is present at the bottom here. It is not very soluble in aqueous water. Water at 25 degrees Celsius did not dissolve a lot of calcium hydroxide in 100 milliliters of water. To compare how solubility of calcium hydroxide changes, we will bring in another solution over here, which is nitric acid. This nitric acid that we have over here has a concentration of 0.01 moles per decimeters cube. This has a concentration of 0.01 moles per decimeters cube. So this is an acid solution, and the calcium hydroxide that we will be adding to this is going to be a base. Between acids and bases, there will be always a reaction. So calcium hydroxide will react with the nitric acid to form calcium nitrate and water. The 1 gram of calcium hydroxide that we are going to be adding to this nitric acid solution will mostly dissolve in this solution, leaving behind only a small amount of calcium hydroxide undissolved in this medium. It will not look exactly like this water and calcium hydroxide solution that we have over here. It's more of a suspension rather than a solution, because there is only a very small amount of calcium hydroxide that we have here in this particular solution. Nonetheless, this is a saturated solution of calcium hydroxide. But if you add exactly the same mass of calcium hydroxide to this nitric acid solution, you will see more of calcium hydroxide will dissolve in nitric acid. This is because nitric acid has H plus ions in the medium, which will react with the OH minus ions that will come in to the medium when calcium hydroxide dissolves in the medium. So I told you calcium hydroxide has an equilibrium between solid calcium hydroxide and Ca2 plus ions and OH minus 2 plus ions in the medium. When H plus ions are present in this nitric acid medium, OH minus ions that came to the medium through calcium hydroxide will react with H plus. So therefore, OH minus ion concentration will go down in our solution that we have over here. And when that happens, equilibrium position of calcium hydroxide solubility is going to be moving to the right hand side, dissolving more and more calcium hydroxide in the medium. So students, in this particular solution, you will notice a little bit more calcium hydroxide will dissolve. So we will take another watch glass and we will measure 1 gram of calcium hydroxide. So the watch glass weight measurement is given here. We will use the tare function to bring the reading of the digital balance to 0, and then I will be adding roughly 1 gram of calcium hydroxide. We have measured exactly 1.02 grams. This was the same measurement as before. And we will add this mass of calcium hydroxide now to nitric acid. So this is a dilute nitric acid solution. So not all of the calcium hydroxide is going to be dissolved in this dilute solution. However, some of the calcium hydroxide will dissolve in this nitric acid to neutralize the acid that is present in this medium. And if there are additional amount of calcium hydroxide that is going to be remaining, that will be observed at the bottom of our solution over here. So let's add our calcium hydroxide solid into our nitric acid. So we have roughly added around 1 gram of calcium hydroxide to our solution over here. And we have washed our stirring rod and we'll dry it using a paper towel. And then we will mix this calcium hydroxide and you will observe, compared to the water solution, some of the calcium hydroxide has additionally dissolved in this medium. You will only be able to observe it when all of these calcium hydroxide that is now suspended in the medium comes to the bottom of this solution. So as a comparison, we will keep these two solutions together and we will move on to a higher concentration of nitric acid. So nitric acid is a strong acid and the concentration of the nitric acid that we have over here is 0.1 moles per decimeters cube. So we can actually calculate the pH of this solution as well, and we can calculate the pH of the previous solution also. So when the nitric acid concentration is 0.1 moles per decimeters cube, since nitric acid dissociates to form H plus and nitrate ions, the H plus concentration is going to be 0.1 moles per decimeters cube. And using our pH calculations, you will be able to obtain the pH value of this solution. The pH value of the solution that I just took over here is going to be 1. Since the nitric acid concentration is 0.1, pH of this solution is going to be 1. And pH of the previous solution that we added calcium hydroxide to is going to be 2. Since the concentration of the nitric acid, initial concentration of the nitric acid was 0.01, so before we added the calcium hydroxide to it, the initial pH value would have been exactly 2. So before we added the calcium hydroxide, the initial concentration would have been 2, and over here we have a nitric acid solution that has a pH value of 1. And apart from that, we have another nitric acid solution that has a pH of 0. So these three nitric acid solutions have different pH values. Before adding calcium hydroxide, the nitric acid solution with 0.02 moles per decimeter cube concentration had a pH of 2, and then before adding calcium hydroxide, the nitric acid with 0.1 moles per decimeter cube concentration had a pH of 1, and then finally we have a solution with 1 moles per decimeter cube concentrated nitric acid, and the pH of that is going to be extremely low, which is pH 0. So this is very acidic. So let's add to the other two solutions as well and observe the solubility of calcium hydroxide in those two solutions. So we will take another watch glass and we will place it on the digital balance and use the tare function to get to the 0 reading, and then we will transfer roughly 1 gram of calcium hydroxide to the watch glass. And then I'm going to transfer this 1 gram of calcium hydroxide onto our nitric acid solution that has a concentration of 0.1 moles per decimeters cube. You can see the calcium hydroxide dissolves somewhat better, or it dissolves well in this nitric acid solution. We will take our stirring rod, we will wash it with distilled water, we will dry it with a paper towel, and then we will stir this solution over here. And as you can see, we saw as we added the calcium hydroxide, majority of it dissolved well in this 0.1 moles per decimeters cube nitric acid solution. So in this case, you will see when the precipitate settles to the bottom that the calcium hydroxide has dissolved more in our 0.1 moles per decimeters cube nitric acid solution. To very clearly observe the solubility of calcium hydroxide in 1 moles per decimeters cube of nitric acid, and to very clearly observe the solubility of nitric acid in these three different solutions, we are going to add 1 gram of calcium hydroxide to this solution, where the concentration is going to be 1 moles per decimeters cube. Now let's take another clean watch glass. We will place the watch glass on the balance, and then we'll use the tare function, and we will add roughly 1 gram of calcium hydroxide to the watch glass. We have around 1 gram of calcium hydroxide here. Now we have measured 1.05 grams of calcium hydroxide to our watch glass, which is roughly around 1 gram. Now you will see when we add this mass of calcium hydroxide to the nitric acid that we have over here, whether we are going to be able to completely dissolve this 1 gram of calcium hydroxide or not. So we will wash our stirring rod, then we will stir the solution. You will see as we stir the solution, majority of our calcium hydroxide, in fact all of the calcium hydroxide we added to our nitric acid solution will dissolve in the solution over here. As I mentioned earlier, nitric acid is a strong acid, and in this solution we have a really high concentration of nitric acid. In this solution we have a really high concentration of nitric acid, which is going to be 1 mole per decimeters cube, and we have 100 milliliters of solution here. So students, we observe that all of the calcium hydroxide that we added to this nitric acid solution completely dissolved in that solution. Why is that? When it comes to dissolving calcium hydroxide in this volume of water that we initially took, we saw majority of the calcium hydroxide did not dissolve in this 100 milliliters of water. However, when we shifted to nitric acid, I mentioned the solubility of calcium hydroxide in nitric acid solutions are going to gradually increase. This is because we have taken 3 concentrations of nitric acid ranging from 0.01 all the way up to 1 moles per decimeter cube concentrated nitric acid. Since nitric acid is a strong acid, when calcium hydroxide is added to nitric acid, calcium hydroxide reacts with the nitric acid and therefore will get dissolved more in the nitric acid solutions. When it comes to the final solution we had over here, the concentration of nitric acid was extremely high. Actually, when we were moving from 0.01 to 0.1 and then to 1, we were multiplying the concentration of nitric acid by a factor of 10. So the number of moles of nitric acid in each of these solutions were multiplied by a factor of 10. So therefore, students, because of this reason, the number of moles of calcium hydroxide that was present in 1 gram of calcium hydroxide was not nearly sufficient enough to react with the number of moles of nitric acid in this particular solution of nitric acid. We have a really high concentration of nitric acid. So therefore, the number of moles of nitric acid in this solution was really high, and the amount of calcium hydroxide that was present in 1 gram of calcium hydroxide was really low. So calcium hydroxide completely reacted with the nitric acid in the medium and completely dissolved in this solution. So the solubility of calcium hydroxide does depend on pH, and we can very clearly observe it without moving on to a titration even, because we can very clearly see that the solubility of calcium hydroxide gradually increased as we increase the concentration of the nitric acid or as we decrease the pH of each of these solutions. So we will mix them really well one more time, and we will keep them aside covered with a petri dish so that they can obtain an equilibrium between hydroxide ions, calcium 2 plus ions, and calcium hydroxide solid. So we will move them out of the main area of our workbench, and we will close each of them with the use of a petri dish. And then we will take our sodium hydroxide solutions. So students, in this case, these two solutions have sodium hydroxide in it. One has a concentration of 0.05 moles per decimeters cube, the other one 0.025 moles per decimeters cube. So in these solutions, we have sodium 1 plus ions and hydroxide ions in the aqueous medium. And when we add calcium hydroxide to these, you will observe the solubility of calcium hydroxide will not be that high. This is because, students, calcium hydroxide equilibrium equation, if you observe it, contains hydroxide ions on the right hand side. So when you increase the concentration of hydroxide ions in the medium, the equilibrium will start to shift to the left where there is more calcium hydroxide solid. So at that point, students, instead of dissolving more and more calcium hydroxide in these two mediums, you will observe the solubility of calcium hydroxide is going to be low, as these two mediums have hydroxide ion, which is going to be considered a common ion, because hydroxide ion is also seen in the equilibrium equation of calcium hydroxide solubility. So calcium hydroxide solid is going to dissociate into calcium 2 plus and hydroxide ions, and then these two will join together to form calcium hydroxide solid again. So in this equilibrium equation, you will have hydroxide ions, which is going to be present in these sodium hydroxide solutions as well. So this is a common ion that is present in calcium hydroxide solutions as well as the sodium hydroxide solutions. So due to this common ion, we have an effect known as the common ion effect. So as you increase the concentration of the hydroxide ions, you will see that the equilibrium will shift to the left, making calcium hydroxide less soluble in these solutions. So students, now you know what will happen to the solubility of calcium hydroxide in theory. Now it is time for us to measure a very small amount of calcium hydroxide, which is 1 gram of calcium hydroxide, and we'll try to dissolve 1 gram each in each of these solutions. Unlike in the previous instance, we will not be visually able to tell whether more or less calcium hydroxide dissolved in the medium. When it comes to the previous instance, especially in the last highest concentration of nitric acid solution, we saw all of the calcium hydroxide dissolved, but unfortunately we will not be visually able to say in which solution calcium hydroxide dissolves more. However, through our calculations, through our titrations, we will be able to comment on that after the titrations are carried out. So let's measure 1 gram of calcium hydroxide. We have measured roughly 1 gram of calcium hydroxide here. Let's add this to our 0.025 moles per decimeters cube concentrated sodium hydroxide solution. You will observe now that calcium hydroxide is not very soluble in sodium hydroxide. Calcium hydroxide was increasingly more soluble in nitric acid when the nitric acid concentration was gradually increased. However, we observe now when it comes to calcium hydroxide being dissolved in sodium hydroxide, calcium hydroxide is not very soluble in sodium hydroxide. Now, let's measure another 1 gram mass of calcium hydroxide, and we will add it to our 0.05 moles per decimeter cube concentrated sodium hydroxide solution. We have a new watch glass here. We will measure roughly 1 gram of calcium hydroxide. We have measured 1.03 grams of calcium hydroxide. We will now add this to our 0.05 moles per decimeter cube concentrated, 0.05 moles per decimeter cube concentrated sodium hydroxide solution. Each time when you are using the same stirring rod, make sure to wash it with distilled water and then use it for other solutions. Otherwise, you might introduce different concentrations into each of these different solutions. For example, if you stir the 1 mole per decimeter cube concentrated nitric acid and then bring it straight into sodium hydroxide, the nitric acid and sodium hydroxide will react, or we can say that the sodium hydroxide solution might get contaminated by nitric acid that is present in the stirring rod. You can mix this solution really well. You will observe majority of the calcium hydroxide is not dissolved. So in the previous suspension, you can see majority of the calcium hydroxide has now gotten collected at the bottom, indicating that majority of the calcium hydroxide that we added did not get dissolved in that medium. Over here also we can very clearly observe majority of the calcium hydroxide did not get dissolved in sodium hydroxide that we have over here as well. So these two sodium hydroxide mediums are not going to be dissolving calcium hydroxide very well. However, there will be a very small portion of calcium hydroxide that dissolves in these mediums, and you will see an equilibrium between calcium 2 plus ions, hydroxide ions, and solid calcium hydroxide that is present in these beakers. So we will keep these beakers aside. We will allow these two solutions to acquire an equilibrium with the solid calcium hydroxide that is present in those beakers. Now we will be moving on to calcium chloride. We have two solutions of calcium chloride. This one has a concentration of 0.025 and this one has a concentration of 0.05. So in these two solutions, we also have another common ion that we see in a solution of calcium hydroxide. As you know, calcium hydroxide dissociates to form calcium 2 plus and hydroxide ions. Although calcium hydroxide dissociation is very low, you will have calcium 2 plus ions and hydroxide ions coming into the medium when you dissolve calcium hydroxide solid in water. In these two aqueous mediums, we have calcium chloride dissolved, meaning these two mediums will have small amount of calcium 2 plus ions in them. Calcium 2 plus is a common ion that is seen in our calcium hydroxide equilibrium as well. So as I mentioned earlier, when the calcium 2 plus ion concentration increases, according to Le Chatelier's principle, the equilibrium position will be shifting to the left, producing more and more solid calcium hydroxide. So in the equilibrium where calcium hydroxide dissociates to form calcium 2 plus and hydroxide ions, when the calcium 2 plus ion concentration increases, the equilibrium position will shift to the left, producing more and more calcium hydroxide, or in other words, decreasing the solubility of calcium hydroxide in these two mediums. So students, let's move on to adding 1 gram of calcium hydroxide to each of these solutions as well. We have measured 1.00 grams of calcium hydroxide. We will add this mass of calcium hydroxide to our calcium chloride solution with a concentration of 0.025. We will stir this solution really well. At this point, you will observe that majority of the calcium hydroxide solid does not dissolve really well in this solution. Instead, it is only going to be suspended in this aqueous medium for a while, and then it will get collected at the bottom. Only a very small portion of the calcium hydroxide we added will get dissolved in this medium. This is because, as I mentioned, is due to the presence of calcium 2 plus aqueous ion that is present in the medium. So due to the common ion effect, the solubility of calcium hydroxide is going to be reduced in this medium. Then we can move on to measuring another 1 gram portion of calcium hydroxide here. Now we have measured 1.01 grams of calcium hydroxide. We will transfer this mass of calcium hydroxide into our calcium chloride solution with a concentration of 0.05, 0.05 moles per decimeters cube, and then we will stir it really well. You can observe majority of the calcium hydroxide we added into this solution as well did not dissolve in the solution. This is because, again, due to the presence of the common ion calcium 2 plus. So due to the common ion effect, we observe that majority of the calcium hydroxide we added into our calcium chloride solutions did not dissolve really well. So we will set them aside for a while so that they can obtain an equilibrium at this temperature. And now we will be moving on to adding calcium hydroxide to water that is at 50 degrees Celsius and to water that is at 90 degrees Celsius. So we have a beaker with the label 50 degrees Celsius, and at this point in time this beaker contains water at 25 degrees Celsius. So we have to increase the temperature all the way up to 50 degrees Celsius, and we can do so with the use of this setup. So we will first fill this water bath with water, and then we will turn it on, and we will place this beaker in the water bath, and we will bring the temperature to 50 degrees Celsius. And when it is at 50 degrees Celsius, we will come back to observe the solubility of calcium hydroxide in water at 50 degrees Celsius. Now students, we are coming back to you after placing the beaker that contains 100 milliliters of water in our water bath, and now the temperature of this water has come up to 50 degrees Celsius. We will stir it one more time and observe the temperature. Temperature is at 50 degrees Celsius. You also will be able to observe the temperature. It is at 50 degrees Celsius. Now, since the temperature is at 50 degrees, before it go above 50 degrees in temperature, we can remove the heat source, and then we can move on to measuring 1 gram of calcium hydroxide. We will place our watch glass here. We will use the tare function to get to a 0 reading, and then we will measure exactly 1 gram. In this case, students, we don't need to be that precise, so we don't actually need exactly 1 gram of calcium hydroxide. We can measure roughly 1 gram of calcium hydroxide. So we have measured roughly 1.06 grams of calcium hydroxide, and then we can remove this beaker from our setup over here. Now this is at 50 degrees Celsius, so handle it with care when you are conducting the experiment, since this is at 50 degrees Celsius. Now students, we are going to add our 1 gram of calcium hydroxide to this beaker where the temperature of the water is 50 degrees Celsius. So students, after adding 1 gram of calcium hydroxide to this water sample that has 100 milliliters of water at 50 degrees Celsius, we need to stir this solution. In order to stir, we can use a stirring rod, and make sure the stirring rod is cleaned before you use it. Then you will stir it until you can observe that all of the calcium hydroxide is suspended in the aqueous medium, but you'll have to continue to stir it really well. So students, after adding calcium hydroxide to this volume of water that is at 50 degrees Celsius, we will mix it really well to maximize the solubility of calcium hydroxide. However, students, we know calcium hydroxide is not going to be very soluble in water, but when we change the temperature, we might have a different solubility of calcium hydroxide. So, to observe the solubility of calcium hydroxide at 50 degrees Celsius, we need to allow the calcium hydroxide solid to establish its equilibrium at that temperature. So, we need to make sure that this calcium hydroxide and water mixture is going to be kept at 50 degrees Celsius. So we need to ensure that this contents in this beaker is allowed to come to an equilibrium at exactly 50 degrees Celsius. So we can do this by again placing this in a water bath and regularly maintaining the temperature of the water bath at 50 degrees Celsius. You can use a temperature controlled oven for this purpose, or you can use a hot plate where you can set the temperature to exactly 50 degrees Celsius. After we have maintained that temperature until this saturated solution of calcium hydroxide has obtained its equilibrium, we can then move on to the titration between this saturated solution and HCl. So students, we will allow this reaction mixture to obtain its equilibrium at 50 degrees Celsius, and then we will come back to you after it has obtained its equilibrium. So we will allow it to stay in the same temperature for a period of time, and after we have obtained this equilibrium, then we will be coming back to you with this solution. So let's move on to the next sample of water until this volume of water containing calcium hydroxide obtains its equilibrium. Now we will be moving on to another 100 milliliter volume of water that is in this beaker. We have exactly 100 milliliters of water measured into this beaker, and we need to bring the temperature of the water in this beaker to 90 degrees Celsius. In order to do that, we will use a water bath that we have over here. So let's first fix this beaker in this setup that we have over here. Right now, the temperature of the solution is not at 90 degrees Celsius. It is somewhere around 29 degrees Celsius. Now it is getting heated up. So it is now at 32. So you can observe the temperature going up gradually as we heat it. Now students, you can see as we heat this water using a water bath, the temperature of this water increases gradually. So we need to increase the temperature all the way up to 90 degrees Celsius, students. So when the temperature of this water is at 90 degrees Celsius, we will come back and we will add calcium hydroxide to that sample of water. It was around 40 degrees Celsius when we last checked. So now, until it reaches to 90 degrees Celsius, we will be measuring the 1 gram of calcium hydroxide we need to add to this volume of water. So first, let's take a watch glass, and then we will place it on the digital balance over here. Then we'll use the tare function to get to a 0 reading. And then we will measure exactly, actually we will measure roughly 1 gram of calcium hydroxide. We have measured 1.06 grams of calcium hydroxide, and now we will wait till the temperature of this water comes up to 90 degrees Celsius, and when it is at 90 degrees Celsius, we'll come back and we will add this 1 gram of calcium hydroxide onto our 100 milliliter water that is at 90 degrees Celsius. Now students, the solution has obtained the 90 degree Celsius temperature that we were trying to obtain. We will check the temperature one more time. The temperature is at 90 degrees Celsius. Please observe this temperature here. It's at 90 degrees Celsius. So after getting this water or volume of water up to 90 degrees Celsius, we can now remove the heat source and we can turn it off. After that, we can proceed to remove our beaker from the setup. It's really hot at this point, so handle it with care. And as you can see, it's at 90 degrees Celsius. After taking the solution out of the water bath, we can proceed to quickly adding our calcium hydroxide before the temperature drops significantly below 90 degrees Celsius. After adding 1 gram of calcium hydroxide, we can proceed to stir our solution using a stirring rod. After stirring this calcium hydroxide and water mixture for a while, we are going to again place this 100 milliliter volume of this solution in a water bath, and we are going to maintain the temperature at 90 degrees Celsius until calcium hydroxide obtains its equilibrium between calcium 2 plus ions and hydroxide ions in the medium. Like I mentioned earlier, calcium hydroxide solubility depends on temperature as well as KSP, or solubility product of calcium hydroxide, depends only on temperature. So solubility product only changes when the temperature is altered. However, when solubility product is altered or changed, the solubility of calcium hydroxide will also change. So to obtain a saturated solution of calcium hydroxide at 90 degrees Celsius, we will place this again at 90 degrees Celsius water bath so that we can maintain a 90 degrees Celsius temperature in this mixture that we have over here. And after it has obtained an equilibrium between calcium hydroxide solid, calcium 2 plus, and hydroxide ions in the medium, we will come back and we will use that saturated solution to carry out a titration. So we are going to place this beaker in a water bath, and we will come back with the next step of our experiment. Students, in the previous part of this experiment, we observed how to prepare 10 different solutions of calcium hydroxide. These calcium hydroxide solutions are not just any calcium hydroxide solutions. Those solutions were saturated calcium hydroxide solutions. In certain solutions, we changed the temperature. In certain solutions, we changed the pH. And in certain solutions, we included common ions. Nonetheless, all of the solutions we formed were saturated calcium hydroxide solutions. So, in a saturated calcium hydroxide solution, you usually always have a small amount of solid calcium hydroxide that is not dissolved at the bottom of the beaker. So, in all of these solutions, you will see at the bottom of the beaker, you always have a very small amount of solid calcium hydroxide that is not dissolved. But there is one exception, students, that is with nitric acid solution we have over here. We can see this is nitric acid with a bit of a high concentration, 1 mole per decimeters cube concentrated nitric acid. When we added calcium hydroxide to it, all of the calcium hydroxide we added reacted with the nitric acid that was present in excess in this medium. So therefore, we do not see a small amount of solid calcium hydroxide at the bottom of this beaker. However, when we dilute the nitric acid concentration, you can see that there is a small amount of calcium hydroxide present at the bottom of each beaker. So this indicates that solubility of calcium hydroxide changes when we change the pH, when we change the common ion concentration, and when we change the temperature as well. But the main point to be taken here is the fact that when it comes to very concentrated nitric acid solution, we do not form a saturated calcium hydroxide solution here, but all of the other solutions, like the ones that we have over here, all of them. If you talk about the others that we have over here also, sodium hydroxide, 0.025 moles per decimeters cube sodium hydroxide solution, when it was added with calcium hydroxide, we have a small amount of calcium hydroxide remaining at the bottom, indicating we have formed a saturated solution. So is this sodium hydroxide solution. And I also emphasized on the fact that when it comes to forming these saturated solutions, the amount of calcium hydroxide that dissolves in each of these different solutions will vary based on the based on whether we have common ions or whether we have different pH values. So if you're talking about sodium hydroxide, when it comes to sodium hydroxide, we have the common ion hydroxide in it, and we can see when it comes to 0.025 concentrated sodium hydroxide solution, we have a smaller hydroxide ion concentration when compared to a solution of sodium hydroxide that has a concentration of 0.050. So more calcium hydroxide will dissolve in this 0.025 moles per decimeters cube concentrated solution than in this, which is 0.05 moles per decimeters cube concentrated sodium hydroxide solution. And you might be able to observe that as well. I'm not very sure whether you will be able to visually observe it when you see it through a camera. However, we can observe if you actually conduct this experiment, you will be able to observe that the layer of calcium hydroxide that is collected at the bottom, layer of solid calcium hydroxide that is remaining at the bottom of these beakers, are not equal. Although the two beakers are similar, you can see in beaker number 1 that we have over here, there's only a small layer of calcium hydroxide compared to the beaker that contains 0.05 moles per decimeter cube concentrated sodium hydroxide. Right, there is ever so slightly a difference in the thickness of the solid calcium hydroxide that is collected at the bottom of each beaker. And this indicates when it comes to 0.02 moles per decimeter cube concentrated sodium hydroxide solution, that solution dissolved only a very small amount of calcium hydroxide compared to the solution that had a sodium hydroxide concentration of 0.025. So as the common ion concentration increased, as I explained earlier, according to Le Chatelier's principle, the reverse reaction was favored when it comes to talking about dissociation of calcium hydroxide into calcium 2 plus and hydroxide ions. The reverse reaction was favored when the hydroxide ion concentration was high. So because of that, equilibrium position got shifted to the left hand side, where more and more calcium hydroxide solid will be formed, which results in dissolving only a very little amount of calcium hydroxide. So in the solution where the common ion concentration is high, we have only a very small amount of calcium hydroxide dissolved. So this is not going to be the main reason we conduct this experiment. We can't just observe with our eyes and say, when it comes to one solution, we have more of a number of calcium hydroxide dissolved, and the other we have lower number of calcium hydroxide dissolved. Instead, we are going to actually move on to a titration to accurately calculate the amount of hydroxide ions present in the medium, which will lead to finally calculating the KSP value of calcium hydroxide in aqueous medium, and then which will allow us to determine the amount of calcium hydroxide that was actually dissolved in each of these different mediums. So now let's move on to first taking one of these solutions and filtering it, because we will need to take small aliquots, 25 cubic centimeter aliquots of each of these solutions to carry out our titration. Therefore, we will have to first filter these solutions. So we have a filtering setup over here, and you have learned how to set up a filtering setup like this in the previous experiments. So we are going to first take our sodium hydroxide solution, 0.025 moles per decimeter cube concentrated solution where calcium hydroxide is also dissolved in this. So we will first filter this solution, and then afterwards we will withdraw a 25 milliliter aliquot of the solution and move on to titration. Now students, we will be carrying out this filtering process for the rest of the solutions as well. However, since it is going to be a repetition of the same process, we will not be showing it on camera when it comes to all of the other solutions. However, keep in mind, when it comes to all of the other solutions as well, we will be carrying out this filtering step. So to show you how the filtering is done, we have our sodium hydroxide solution in which we have dissolved 1 gram of calcium hydroxide, and now we will carefully filter this solution. If you want to direct the aqueous solution directly to the filter paper, we can use a glass rod like so. And as you can see, the solution is getting filtered and is getting collected at the beaker we have placed at the bottom of the funnel. So after the solution is filtered, we are going to be withdrawing 25 milliliter aliquot of this saturated calcium hydroxide solution. Now, please observe how this calcium hydroxide solution is getting filtered, and keep in mind, students, at the bottom what we have is saturated calcium hydroxide solution. The only difference is we are going to remove this additional calcium hydroxide solid that is present at the bottom of the beaker, because when we try to remove exactly 25 cubic centimeters of this solution, there might be some calcium hydroxide solid particles that enter our 25 milliliter aliquot, which could result in errors when we are titrating the saturated calcium hydroxide solution. So to prevent any errors, we will be filtering each of these solutions with the use of our filtering setup like this, and then we will come and carry out a titration to find out the amount of HCl needed to titrate the OH minus ions that are present in each medium. Now students, we will come back after our first solution, which is calcium hydroxide dissolved in 0.025 moles per decimeter cube concentrated sodium hydroxide solution is filtered using this setup. Students, we will meet you after this filtration is complete, and then we will be moving on to a titration. Now students, we have filtered off our calcium hydroxide solution that was made by dissolving calcium hydroxide solid in 0.025 moles per decimeter cube concentrated sodium hydroxide solution. So we have the filtrate here, and now we will use a pipette to withdraw 25 cubic centimeters of that filtrate into each of these titration flasks. So keep in mind, students, this filtrate has saturated solution of calcium hydroxide, and we will be titrating to understand how many moles of hydroxide ions are present in the medium, and using that information as well as the concentration of the initial sodium hydroxide sample, we will be able to calculate the amount of calcium hydroxide that dissociated and came into the medium as calcium 2 plus ions and hydroxide ions. So let's first take 25 milliliters of this saturated calcium hydroxide solution with the use of this pipette. And then we'll be transferring it into this titration flask. I hope you remember, if you have a drop of solution remaining at the edge or remaining at the tip of the pipette, you do not blow it out, because this pipette is calibrated in such a way that there is going to be a small drop remaining at the tip of the pipette. So you are not supposed to blow it out, so keep that in mind. And then we will move on to the next titration flask. we have measured yet another 25 cubic centimeter aliquot of saturated calcium hydroxide solution, and we'll repeat the same process for the third titration flask as well. Right. Now we will be transferring this to a titration flask like so. And afterwards we can keep our pipette and titration flasks to a side. We can remove this as well. And now, students, we have to move on to the actual titration. So here we have our burette, which is filled all the way up to the zero line using 0.1 moles per decimeters cube concentrated HCl solution. So this is filled all the way up to the zero line. And then we are going to take one of our 25 milliliter aliquot of the calcium hydroxide solution that we took into each of these titration flasks, and then we will add a few drops of phenolphthalein into each of these flasks, and we'll mix it really well. And you can observe, as soon as we added phenolphthalein, the solution turned to a pink color. You can observe that pink color very clearly when we place this titration flask on a white color background. So this pink color is there because we have over here a sodium hydroxide solution, and in this sodium hydroxide solution we have dissolved calcium hydroxide as well. So we have produced a saturated calcium hydroxide solution with the use of a sodium hydroxide solution, and the concentration of the sodium hydroxide solution we used was 0.025 moles per decimeters cube. So this is definitely an alkaline medium, and that is why phenolphthalein gave this particular color. Now we will be starting the titration with the use of 0.1 moles per decimeters cube concentrated HCl solution. So I hope you remember how to carry out a titration and how to hold a burette. So when you're holding the burette, do not open it and close it, or open the stopcock and close the stopcock using your right hand or your more dominant hand. Your more dominant hand is reserved for swirling the titration flask around, and using your left hand, in this case, you will be using the left hand to open and close the stopcock the way that I'm showing you right now. So let's start our titration. We will add HCl little by little, and you will notice gradually the color of the solution is starting to decrease as we add HCl, and at one point this pink color will completely disappear. At that point we will stop our titration and we will take the burette reading, which is going to be our endpoint. So we are close to the endpoint. We will gradually add HCl. So we have a very light pink color compared to the pink color we started off with. We can add a few more drops. we can still see a slight pink color. However, I'm certain with just one more drop, it will be completely colorless. So we have now added just one more drop. At that point, you can observe that the solution is completely colorless. Now, at this point, you will have to take the burette reading. So, our burette reading is over here, students. Since I can't see, I will bring this burette down to my eye level, actually around here. So the burette reading is 7.9 cubic centimeters. So the burette reading is 7.9 cubic centimeters, or 7.9 milliliters. So with that in mind, we can now move on to our next titration. Now students, we move on to our second titration. So we will take our second aliquot of 25 cubic centimeters of the solution we took, and then we will add few drops of phenolphthalein indicator. Since this is an alkaline medium, like I mentioned earlier, you will see a nice pink color as you add our phenolphthalein indicator to this solution. And our initial reading is 7.9, and then we will start our titration from that initial reading. So after we obtain a final reading, we are going to subtract the initial reading to obtain the volume of our HCl that was added to titrate this 25 milliliters of saturated calcium hydroxide solution we prepared earlier. So since we have greatly reduced the pink coloration we can see in this titration flask, meaning with just 1 or 2 drops of sodium hydroxide, this will turn colorless. Let's add one more drop of sodium hydroxide. Still, there is a very slight pink coloration. We will have to add one more drop of sodium hydroxide to completely make that pink color disappear. At this point, the entire solution is very clearly no longer pink, indicating we have obtained our end point. So let's take a look at the final reading over here. So the final reading is 15.7. So the final reading is 15.7. We started off at 7.9 and we have 15.7 as the final reading. So if you subtract 7.9 from 15.7, the answer is 7.8. So we have added 7.8 milliliters of HCl into our second titration flask. So the first titration we spent 7.9 milliliters of HCl. In our second titration, we have added 7.8 milliliters of HCl into the titration flask. These two readings are concordant. Now we will be moving on to our third titration. Now we move on to the third titration. So we are repeating the same titration 2 more times. So this is the third titration. Like we did in the previous instances, we will add a few drops of phenolphthalein indicator into our titration flask here. So since the solution is alkaline, you will observe solution turning a pink color. And then we will start to titrate this solution with 0.1 moles per decimeter cube concentrated HCl solution. Our initial reading is 15.7 So from 15.7 onwards, we will be starting to add HCl over here. So initial starting butyrate reading is 15.7. We still have slight pink color in the medium. We will add few more drops to see if the pink color completely disappears. And at the point at which the pink color completely disappears, we will take the butyrate reading. I think we need one more drop to completely make the solution colorless. So we now have made this solution completely colorless by adding that last drop of HCl. The reading as it stands is 23.6. So the butyrate reading is 23.6, students. We started off with 15.7 and now we have butyrate reading 23.6. So the amount of HCl that is added to this titration flask is 7.9 cubic centimeters or 7.9 milliliters of HCl. So we have three readings obtained for our first solution, and they were 7.9, 7.8 and 7.9 again. All three readings are concordant. So while noting this down, we can now move on to a new solution. Students, now we are moving on to our second set of titrations. In this second set of titrations, we have here the filtered saturated calcium hydroxide solution that was prepared by dissolving calcium hydroxide in 0.05 moles per decimeter cube concentrated sodium hydroxide solution. So the filtered saturated calcium hydroxide solution is over here, and we have a butyrate which is cleaned, and we have three clean titration flasks as well. So we will now take 25 cubic centimeters of this solution into our pipette, and after making sure the meniscus aligns well with the calibrated mark over here, we will transfer this 25 milliliter volume of our solution into our first titration flask. And then we will repeat this process 2 more times for the other 2 titration flasks as well. Now we have added 25 cubic centimeters of saturated calcium hydroxide solution into each of these titration flasks. And then we will add few drops of phenolphthalein indicator, and we will mix the indicator really well. You can see a very nice pink color is observed because this medium is alkaline, and the concentration of sodium hydroxide ions here is higher than the first titration that we did. That solution was made using 0.025 moles per decimeter cube concentrated sodium hydroxide, and over here our calcium hydroxide solution was prepared by dissolving 0.05 moles per decimeter cube concentrated sodium hydroxide. So therefore, students, we have a higher hydroxide ion concentration here. And now we will start our titration. But before we start our titration, please keep in mind we have filled HCl all the way up to the zero line in our burette. So this burette is refilled all the way up to the zero line. So the initial reading is 0, and then while keeping that in mind, we can start our titration. You can see it takes longer for this titration to happen because we have more hydroxide ions in the medium, so we will end up spending more HCl to titrate this solution. So we have already added 9.5 cubic centimeters of HCl into this titration flask. Observe that the color has not drastically changed here. When it comes to our initial set of titrations, the endpoint was obtained at 7.9 cubic centimeters. So this is a clear indication that the solution has more hydroxide ions. We'll continue to titrate the solution. Make sure to stir the solution really well while you add HCl. So by now we have just a little bit of pink color in the medium. Slight hue of pink is there, so we will be adding just one more drop of HCl very carefully, and then we will stir the solution really well. At this point we can see that there is no trace of a pink color in the medium. So this indicates that we have obtained our end point. So our end point was obtained at 13.9 cubic centimeters. Our end point was obtained at 13.9 cubic centimeters. Now that was our first titration. The same titration will be repeated 2 more times. Now students, we move on to our second titration. So we will add 2 drops of phenolphthalein. Then we'll mix it really well. After that, we will add HCl into this titration flask and we will carry out. After that, we will start our titration. And students, when you're starting the titration, keep in mind our initial titration, we observed that the endpoint was 13.9. So we have our meniscus at 13.9 mark. So our initial reading when it comes to our second titration is going to be 13.9. So while keeping that detail in mind, we can proceed to add HCl to this solution. Since we know where the endpoint is roughly going to be, we can add HCl a little bit faster initially, but towards the end point we have to be more careful and we have to add HCl a little bit more slowly. So students, we are closing in on our endpoint. We can add a few more drops. We'll add one more drop and observe whether there's going to be a very clear color change. We'll add another drop. So we will continue to add HCl drop by drop because we are very close to the endpoint here. You can see there's only a very light pink color in this titration flask. I believe we only need one more drop at this point because there's still a slight pink color in the titration flask. So now we no longer observe any pink color in the solution in the titration flask. So therefore we have obtained our endpoint. At this point we can observe that our end point or final buried reading is going to be 27.8. Our final buried reading is going to be 27.8. So students, when it comes to the initial buried reading, it was 13.9 and now it is 27.8. So if you subtract 13.9 from 27.8, you will obtain 13.9. If you subtract 13.9 from 27.8, the value is going to be 13.9 itself. So when it comes to our second titration as well, we observed that the volume of HCl spent on the second titration was also exactly 13.9 milliliters. So now we can move on to our third and final repeat of this second set of titrations. So let's move on to our third titration now. Now students, we move on to the third and final titration. We have our final aliquot of our calcium hydroxide saturated solution over here. So like we did in the previous instances, we will be adding phenolphthalein indicator to this titration flask or to this solution, and then we will mix it really well, and then we will start our titration. Keep in mind students, when it comes to our second titration, our final volume was 27.8. So in the third titration, so our initial buried reading is going to be 27.8. Now we will slowly add our HCl. Since we know in the previous two instances we obtained an HCl volume of 13.9 as the endpoint, we can be sure that even in this titration we will spend close to 13.9 cubic centimeters of HCl. So in the initial stages we can start to add HCl a little faster. However, as the color of the solution starts to disappear, we can start to add HCl a bit more slowly. We can see the color of the solution has gone down quite a lot. So at this point we will start to add HCl drop by drop. So the color of the solution is almost completely gone, but there is still a very slight pink coloration. I am not 100% certain whether the camera can pick it up. However, there is a slight pink color in the medium. So to eliminate that pink color, we will add just a single drop of HCl, and then we will mix the solution really well. And students, at that point we have obtained our endpoint, because right now the solution is completely colorless. The Bureau reading at this point is, the final Bureau reading is at 41.6. Final Bureau reading is at 41.6. Initial Bureau reading was 27.8, and the final Bureau reading is 41.6. The difference between these two readings is the amount of HCl that we spent over here. So the difference between these two readings is 13.8. Difference between these two readings is going to be 13.8. So students, we have now concluded our second set of titrations. First set of titrations focused on calcium hydroxide dissolved in 0.025 moles per decimeter cube concentrated sodium hydroxide solution. And when it comes to our second set of titration, we focused on titrating a saturated calcium hydroxide solution that was prepared by dissolving calcium hydroxide in 0.05 moles per decimeter cube concentrated sodium hydroxide solution. Now we move on to our third set of titrations, where we will take calcium hydroxide solution that is formed by dissolving 1 gram of calcium hydroxide in 0.01 moles per decimeter cube concentrated nitric acid solution. Now students, we are going to observe the calcium and hydroxide ion concentrations in these solutions that we have prepared earlier. So in a previous step, we prepared a calcium hydroxide solution by dissolving 1 gram of calcium hydroxide in 0.025 moles per decimeter cube concentrated calcium chloride solution. And now, after the solution has reached equilibrium, we have filtered out this solution, and we have that filtered solution in this beaker. So in this part of our experiment, we will remove 25 milliliters of this solution into each of these titration flasks, and then we are going to titrate it with the use of HCl. The concentration of HCl is 0.1 moles per decimeters cube. Now students, when we are talking about titrating this solution with the use of HCl, we will be titrating the OH minus ions in the medium. So the OH minus ion in the medium is going to depend on the amount of calcium hydroxide that has dissociated and come into the aqueous medium. We added 1 gram of calcium hydroxide. So the dissociation of calcium hydroxide will depend on the amount of calcium 2 plus ions in this medium. Why? Because we dissolve the calcium hydroxide in calcium chloride solution. So calcium chloride solution already has a certain amount of calcium 2 plus ions, because calcium chloride will fully dissociate to produce calcium 2 plus ions and chloride ions. So in a solution, concentration of calcium chloride is 0.025. We can be sure in such a solution, the calcium 2 plus ion concentration is going to be 0.025. And in that solution, we have dissolved calcium hydroxide. And students, as I have told you in the previous parts of this experiment as well, calcium hydroxide, when dissociates, it produces calcium 2 plus ions and hydroxide ions. and this is the equilibrium reaction, meaning common ions in the medium will affect the equilibrium. So in this case, calcium hydroxide equilibrium will be affected by the calcium 2 plus ions that is already present in this calcium chloride aqueous solution. So when the calcium 2 plus aqueous ion concentration is high, calcium hydroxide dissociation will not be favored. Calcium hydroxide turning into calcium 2 plus and hydroxide ions is going to have an equilibrium, and when the calcium 2 plus concentration is high, according to Le Chatelier's principle, equilibrium will be shifted to the left, and this will create more and more calcium hydroxide to stay as a solid instead of coming into the medium as aqueous ions after dissolving in the medium. So we are going to observe whether this common ion effect can very clearly be seen in these two aqueous solutions. We have another calcium chloride solution with a higher concentration, and we have dissolved the exact same amount of grams of calcium hydroxide in it. So after carrying out the titrations, we can compare the readings and see which of these solutions had more of a hydroxide ion concentration. Having a higher hydroxide ion concentration would indicate that more calcium hydroxide dissolved in that solution. So with that information, we can now proceed to withdrawing 25 milliliters of calcium hydroxide solution that we have prepared by dissolving 1 gram of calcium hydroxide in 0.025 moles per decimeter cube concentrated calcium chloride aqueous solution. So we will be using a 25 milliliter pipette for this purpose. This is a washed 25 milliliter pipette. So we will now proceed to withdraw 25 milliliters of our calcium hydroxide solution. We have measured exactly 25 milliliters. We can transfer it into our titration flask like so. We will repeat the same process for the other 2 titration flasks as well. As you know, we would normally have 2 repeats for each titration. Altogether, we will obtain 3 readings for each titration so that you can be very sure about the readings you have obtained. So we have now measured again another 25 milliliters of the solution. Now we will transfer it again to our second titration flask. And then we will move on to our final titration flask. We will add 25 milliliters of the solution to the third titration flask as well. Now, students, we have our calcium hydroxide solution that was prepared by dissolving 1 gram of calcium hydroxide in calcium chloride solution. And then we will add our indicator. So we will be titrating the hydroxide ions in the medium. So this medium is alkaline. Now when you add phenolphthalein indicator, what happens? it will turn pink. So we will add 2 drops of phenolphthalein indicator, and you can very clearly see the color of this medium. To clearly see it, we can place it under a white tile. So now you can observe that this particular medium is pink in color. So we have taken this burette and filled it all the way to the zero line with 0.1 moles per decimeters cube HCl solution. So it is now time for us to titrate this solution with our 0.1 moles per decimeters cube concentrated HCl. So we will first start slowly, and you can see as we titrate it, the color does not change drastically, meaning the OH minus ion concentration in this medium is somewhat high. So towards the end of the titration, you would see the color of this aqueous medium, the pink color of the aqueous medium, will gradually decrease, and at one point it will acquire a permanent colorless color, or the solution will permanently be colorless. So at that point we have obtained our end point. You have to keep mixing the contents in the titration flask really well while you are adding HCl little by little. You can see when HCl is added to the medium, around the area where the drop comes into contact with the medium, the color, the pink color, will momentarily disappear. When you're doing the titration, this is one of the observations you will make, but after mixing the solution really well, the entire medium again remains a persistent pink color. But if you add more HCl, you will see this color changing again to a lighter pink shade, and eventually it will be colorless, indicating that we have obtained our endpoint. Now students, we are close to the endpoint. We can observe over here the pink color is very light at this point. So maybe with a few more drops, this pink color will completely disappear. It is still pink in color, however, that pink color may disappear after the addition of few more drops of HCl. Maybe just 2 more drops. So the color is now almost colorless. It is not as pink as it was initially. So at this point, if you add 1 more drop, we might obtain our endpoint. If 1 more drop is not sufficient, we can proceed to add 2. As you can see students, with just the addition of 1 drop of HCl, we have now turned the entire aqueous medium colorless. So this means we have obtained our endpoint. So let's take a look at the reading. The reading is not at my eye level, so I will have to bring it down. So the reading is 7.6. Reading is 7.6 cubic centimeters. So we obtain our first reading for the solution, that is 7.6. We will be repeating this test 2 more times to make sure that the reading that we obtain in the experiment is concordant. So let's move on to the next titration. Now we move on to our second titration. So we have our second aliquot, or 25 milliliters of our calcium hydroxide solution, and before we place it under the burette, we will add our indicator. That is a very important step, students. So we'll have to add, just like in the previous step, we will add 2 drops of phenolphthalein, and we will mix it really well so we can see this nice pink coloration in the aqueous medium. And keep in mind, students, the previous titration gave us an endpoint at 7.6 milliliters or 7.6 cubic centimeters. So now we are starting with that reading. We have not topped it up all the way to 0 since we know that this particular titration also might have the same reading or similar reading to that. We know the burette contains enough HCl to proceed with this titration. So therefore, we will be starting with this initial reading of 7.6, and we will be adding HCl to this second titration flask, and we'll be moving on with the titration to obtain an endpoint like that. So the initial reading is 7.6, keep that in mind, and after we obtain the final reading, we will subtract this initial reading from the final reading to obtain the amount of HCl or the volume of HCl that was added to this titration flask to obtain our endpoint. So let's start the titration. Since we know where the endpoint lies, in the sense, since we know that we have the endpoint obtained somewhere around 7.6, we can proceed to add HCl a little faster than before, and as we close in on the endpoint, we can slow down the addition of HCl. Now we can observe that the pink coloration has decreased, or the intensity of the pink color we observe in this aqueous medium is now somewhat low. So we will be adding HCl a bit slowly from this point onwards, because you can see the pink color of the medium is almost entirely gone. With 1 more drop, we might obtain our endpoint. Let's see. Pink color still persists, so we will continue to add HCl drop by drop until the solution turns colorless. We can still see a pink coloration, so we will add HCl drop by drop until we can no longer see a pink color. I'm not sure whether the camera can pick it up. It is still a little pink in color, I think with one additional drop or one more drop, it will turn colorless. Now students, with that single drop of HCl, the solution has now turned colorless. So it is now time for us to obtain the endpoint. Endpoint is 15.2. Endpoint is 15.2. So the initial reading was 7.6. Now the current reading is 15.2. 15.2 minus 7.6 gives us 7.6 itself. So our second reading is also 7.6. So our initial reading and the second reading both are 7.6. These two readings are obviously concordant. So while keeping that in mind, we can move on to our third titration. And after that, when the third titration is over, we will move on to a different solution. Now we are at our third titration. We will follow the same steps we followed for the previous two titrations. We will add our phenolphthalein indicator. We'll add 2 drops of the phenolphthalein indicator to the titration flask. And then we can proceed to titrate this solution with 0.1 moles per decimeter cube concentrated HCl solution. So students, keep in mind the previous titration, our reading was at 15.2. Our reading was at 15.2. So we are starting with that initial reading. And like we did in the previous titration, after obtaining the end point, we will subtract this initial reading from the final reading to measure the volume of HCl that was actually added to our titration flask. So let's begin our titration. Now we can see that the color of the solution is somewhat lighter now. It's no longer a dark pink color. So we have to now add HCl a bit more slowly so that we can obtain a more accurate endpoint. It is still pink in color. Sometimes students, the camera might not pick up the slight pink hue that is present in the medium. However, when you are actually doing this experiment, when you're doing this titration in the labs, you will be able to notice a slight pink hue towards the endpoint of the titration. So when you're obtaining the endpoint, the solution should completely be colorless. It should not have any traces of pink. So you will have to add one more drop if there is still a little bit of a pink color in the aqueous medium. I know the camera might not pick it up, but this medium is still pink in color. So when you are doing titrations like this in the lab, it is important to keep in mind we need to add the right amount of HCl until you obtain a colorless solution. So you have to add HCl until the aqueous medium is completely colorless. This medium is now completely colorless, students. So at this point, we have obtained our end point. So the final reading that we have over here is 22.9. The final reading that we have over here is 22.9. If you want to see it a bit more clearly, we can use filter paper. So this is the reading. 22.9 is our reading. So our initial reading was 15.2 and the final reading is 22.9. So the difference between these two readings is 7.7. So our final titration indicated that the volume of HCl that we have added for the titration over here is 7.7. Initial reading was 7.6, second reading was 7.6, and the final titration or the third titration reading was 7.7. So while keeping this in mind, we can move on to our next solution. Now students, we move on to the next calcium hydroxide solution. This calcium hydroxide solution that we have over here was prepared by dissolving 1 gram of calcium hydroxide in 0.05 moles per decimeters cube concentrated solution of calcium chloride. So we had a calcium chloride solution that had this concentration, and you saw how we prepared it by dissolving 1 gram of calcium hydroxide in this calcium chloride solution. So the calcium chloride solution already has a higher concentration of calcium 2 plus ions now. So in the calcium hydroxide dissociation, also we will be producing calcium 2 plus. So calcium 2 plus ions can be considered a common ion that is present in this aqueous medium that will affect the equilibrium that exists between calcium hydroxide solid and calcium 2 plus and hydroxide ions in the aqueous medium. So students, like I mentioned in the previous titration as well, when the calcium 2 plus ion concentration goes up, the dissociation or dissolving of calcium hydroxide will be affected. So as the calcium 2 plus ion concentration increases, calcium hydroxide, calcium 2 plus and hydroxide ion equilibrium will shift to the left, making more and more calcium hydroxide solid. So dissolving of calcium hydroxide in this medium will be lowered. At this equilibrium, you would notice that the hydroxide ion concentration is lower than the hydroxide ion concentration in the previous solution. So in this titration, one of the things that you may observe as we are conducting this titration is that we will be spending less HCl to titrate this solution. So that will indicate that only a small amount of calcium hydroxide has actually dissolved in the aqueous medium. We have filtered this calcium hydroxide solution, and the filtered solution is over here, and we will be withdrawing 25 milliliters of this solution into each of these titration flasks. So let's take our 25 milliliter pipette and let's withdraw 25 milliliters of this filtered calcium hydroxide solution into our pipette, and then we can transfer it into our titration flask. And we'll repeat this process for the other two titration flasks as well. Let's remove another 25 milliliter volume from this filtered solution of calcium hydroxide, and let's transfer it into our third titration flask as well. So always make sure the bottom of the meniscus aligns perfectly with the calibrated line of your pipette when you're transferring or when you're measuring volumes using a pipette. I think by now all of you who are watching this would know that. So, but it's just a reminder, whenever you are doing any measurements with the use of volumetric equipment like this, like a pipette, or when you're using burette or a volumetric flasks, make sure to have the bottom of the meniscus perfectly aligned with the calibrated line when you're measuring volumes with the use of volumetric equipment like the ones I mentioned earlier. So now we have measured 25 milliliters of the solution into each of these titration flasks. So let's add a few drops of the phenolphthalein indicator, and then we can start titrating this solution with the use of 0.1 moles per decimeter cube concentrated HCl solution like we did in the previous instance. We will mix the solution well, and then we can start the titration with the use of 0.1 moles per decimeter cube concentrated HCl. So students, we have now filled the burette all the way to the zero line, and when we are starting this titration, we need to make sure that the initial reading is taken down. So the initial reading over here when we are starting this titration is 0, or we have filled HCl all the way up to the 0 line. Now students, when you're doing the titration, it might be sometimes helpful to have an idea about what to expect out of this titration. And in this titration, the common ion, calcium 2+, is present in a higher concentration. So therefore, we know calcium hydroxide is not going to be very soluble in such a medium where the calcium 2+ ion concentration is very high. So calcium hydroxide will not come into the medium that much as calcium 2+ and hydroxide ions, meaning the hydroxide ion concentration in this medium is low. So the amount of HCl that we will be needing to titrate this solution should be less than the amount of HCl that we needed to titrate the previous solution. So let's see if we observe that situation here. So let's start to titrate our solution. We can start adding HCl drop by drop like so. When you're doing the titration, you have to constantly mix the solution. You can see gradually the pink color in the medium is decreasing. Now, the pink color is still there, but with the addition of 1 drop, this pink color might disappear because the pink color is very light here. Maybe it might take more than 1 drop, but we have to start adding HCl very carefully. It's still pink. We'll add 1 more drop. Now the pink color has completely disappeared, students. So at this point, we can take our reading. We have obtained our endpoint. So now it is time for us to observe our first reading. Now students, the reading is over here, so it is above my eye level. So I will be able to bring this down to my eye level so that I can observe the reading correctly. So the meniscus is over here and the reading is 6.6. 6.6. So the reading is 6.6. To observe it a bit more clearly, we can use a white color background as well. It is 6.6. So now we are going to move on to our second titration. Now we move on to our second titration of the same solution. So we have the 25 milliliters of the solution we measured earlier. We have our phenolphthalein, and we will add 2 drops of phenolphthalein like we did before. And we will mix the solution well. And then we can proceed to our titration. So students, again, like I mentioned earlier as well, we need to note down the initial reading. Initial reading is 6.6. So after noting it down, we can proceed to our titration here. Now students, you can observe the color decreasing, and the color has decreased significantly at this point. So we can start to add HCl a little bit more slowly. There is still a slight pink coloration in the medium. We will add a few more drops. At this point, the medium is completely colorless. So the reading right now is 13.1. The reading right now is 13.1. So if you want to observe it a bit more clearly, you can use a white color background. It's at 13.1. And the initial reading was 6.6. Final reading is 13.1. The difference between the two would be 6.5. So the difference between the two is 6.5, and this means for the second titration we have spent 6.5 milliliters of 0.1 moles per decimeter cube HCl. So the first titration we spent 6.6 milliliters, and second titration it was 6.5 milliliters. Now we move on to our third titration. And like we did in the previous 2 instances, we will add 2 drops of phenolphthalein, and then we will mix the solution well. And we can now proceed to titrate this with the same HCl solution we used earlier, and the initial buried reading is going to be 13.1. So the final buried reading in the second titration was 13.1, So that reading will become our initial reading when it comes to the third titration. Now you can see, students, as we add HCl, like in the previous instances, the color, pink coloration, pink color in the medium gradually decreases as we add HCl. Now we are close to the end point. The pink color in the medium is very, very light. So therefore, if we add a few more drops, we will obtain our endpoint. There is still a pink color in the medium. One more drop is required. At this point, we have obtained our endpoint. So let's take a look at the beauty reading at this third titration endpoint. So the reading is 19.5. The reading is 19.5. So the initial reading was 13.1 and the final reading is 19.5. The difference between the two is going to be the amount of HCl that we added into this titration flask. So 19.5 minus 13.1 is 6.4. So the amount of HCl we added to this titration flask to obtain the endpoint was 6.4. So let's go over the three readings we obtained from the three titrations. The first titration reading was 6.6, second one 6.5, and the third one was 6.4. So these volumes are smaller than the volumes that we observed when we were carrying out titration for the previous solution. The previous solution was prepared by dissolving calcium hydroxide in a calcium chloride solution that was having a lower concentration than the solution that we were titrating just now. So, and we can see very clearly when the calcium 2 plus ion concentration in the initial medium was low, the hydroxide ion concentration has been high. That is why when we were titrating the calcium hydroxide solution prepared by dissolving calcium hydroxide in a calcium chloride solution which had a lower concentration, we see that there is a high concentration of hydroxide ions there, indicating calcium hydroxide dissolved in the solution where there was, indicating calcium hydroxide dissolved a little bit more when comparing the two solutions that we observed in this part of the experiment. We had one solution where the calcium chloride concentration was 0.025 and another solution where the calcium chloride concentration was 0.05. So in the second solution that we titrated just now, the calcium ion concentration was high. It was actually twice as high compared to the previous solution. So into these solutions, we added calcium hydroxide and we were trying to observe how much of the calcium hydroxide has dissolved in each of these solutions when we add the same amount of calcium hydroxide to each of these solutions. And when we were titrating the hydroxide ions present in each of these mediums, we saw to titrate the hydroxide ions present in this particular solution, we spent more HCl, indicating that the hydroxide ion concentration in this solution was greater than the hydroxide ion concentration in this solution. This indicates when the calcium 2 plus ions in the medium increases, calcium hydroxide has dissolved less in that medium. Now this can be explained with the use of KSP, as we explained in the theory part of this experiment. So students, since calcium 2 plus is a common ion, you would observe calcium hydroxide dissolves less in a medium where there is a common ion in a higher concentration. So after this observation, we can now move on to our next titration. Now students, we are moving on to a new calcium hydroxide solution that was prepared by dissolving 1 gram of calcium hydroxide in nitric acid solutions. So we observed in the beginning of our experiment, we had 3 different nitric acid solutions, one with a concentration of 1 moles per decimeters cube, the other with 0.1 moles per decimeters cube, and another one with 0.01 moles per decimeters cube. So the concentration was diluted 10 times when it comes to each of the following solutions. Started with 1 moles per decimeters cube, then 0.1, and then 0.01. So we had these solutions and we dissolved 1 gram of calcium hydroxide in each of these solutions. As you know, calcium hydroxide is a base and nitric acid is a strong acid. So when it comes to 100 milliliters of 1 moles per decimeters cube concentrated nitric acid solution, it contains enough and more nitric acid to react with the calcium hydroxide present in 1 gram of calcium hydroxide. So therefore students, when you are trying to dissolve 1 gram of calcium hydroxide in 1 moles per decimeters cube concentrated nitric acid solution, all of the calcium hydroxide dissolves in it. There is no precipitate at the bottom. This indicates that calcium hydroxide that we added completely dissolved in this aqueous medium. But when we diluted the acid and obtained these 2 solutions, when we dissolved calcium hydroxide in it, we saw the solubility of calcium hydroxide in those 2 solutions changed. They are not going to be completely dissolved in each of these mediums. However, solubility depended on the concentration of nitric acid in the aqueous medium. So as nitric acid reacts with OH minus ions in the aqueous medium, OH minus ion concentration will go down. At that point students, you can remember calcium hydroxide and calcium 2 plus and hydroxide ion concentration based equilibrium will shift to the right hand side. So when the equilibrium shifts to the right hand side, what happens is our calcium 2 plus ion concentration goes up. When the hydroxide ion concentration is lowered, equilibrium shifts to the right hand side, making the calcium 2 plus ion concentration go up. So keep in mind, in each of these solutions we have different amount of H plus in the medium, or in other words, we can say the pH of each of these solutions was initially different to one another. When it comes to 1 moles per decimeters cube concentrated nitric acid solution, the pH was 0, and then 0.1 moles per decimeters cube nitric acid, pH was 1, and 0.01 moles per decimeters cube concentrated nitric acid has a pH of 2. So we can say the pH is changing in each of these solutions before we add our calcium hydroxide. So when calcium hydroxide is introduced to these solutions with different pH, you are going to observe how the solubility of calcium hydroxide changed. And we started with 1.0 moles per decimeters cube concentrated nitric acid, and we observed that all of the calcium hydroxide we added dissolved there, and the solubility of calcium hydroxide decreases as we decrease the concentration of the acid. Now calcium hydroxide dissolving in water equilibrium will be shifted to the right hand side. Equilibrium position will be shifted to the right hand side as we remove OH minus ions from the medium by reacting with H plus. So the acid OH plus in this medium will react with the OH minus ions that are coming into the medium when calcium hydroxide dissolves in the medium, and as the OH minus concentration goes down, equilibrium position according to Le Chatelier's principle will shift to the right hand side, increasing the calcium 2 plus ion concentration and decreasing the calcium hydroxide solid in the medium, meaning calcium hydroxide will dissolve in the medium more. So now it is time for us to move on to our titration. Keep in mind, students, we will not be titrating this solution over here, because we know all of the calcium hydroxide dissolved, and not only that, we know all of the calcium hydroxide reacted. How do we know this? Because when it comes to 100 milliliter volume of 1.0 moles per decimeter cube nitric acid, we know that we'll have enough and more nitric acid to react with the calcium hydroxide we are adding. So there will be no excess or additional hydroxide ion in the medium to titrate against HCl. So therefore, we will not be using this solution and carrying out titration with it, because we do know that all of the OH minus ions that came into the medium through calcium hydroxide has now reacted with the nitric acid. Then we have our 0.1 moles per decimeters cube nitric acid, and we have dissolved 1 gram of calcium hydroxide to produce a saturated calcium hydroxide solution, and we have filtered that solution, and the filtrate is present over here. So we saw how it was prepared, and we saw how the filtration is carried out. So that filtered solution is present over here. Now it is up to us to withdraw 25 milliliters of this solution, and we'll be transferring 25 milliliters of this solution into 3 different titration flasks, and we'll be proceeding with the titration. Like in the previous titration, we will be using 0.1 moles per decimeter cube concentrated HCl solution. So let's start the titration. To draw 25 milliliters of this solution, we will be using a pipette like this. Using this pipette, we can withdraw 25 milliliters of this solution. And then we can transfer the 25 milliliters of our saturated calcium hydroxide solution into the titration flask, and we'll repeat this process to the other 2 titration flasks as well. So let's transfer 25 milliliters of the solution into our second titration flask, and we can take our third and final titration flask and do the same to that titration flask as well. Now students, we have taken 25 milliliters of our calcium hydroxide solution that we prepared by dissolving 1 gram of calcium hydroxide solid in 0.1 moles per decimeter cube concentrated nitric acid solution. Now students, let's move on to the first titration. So we will take our first titration flask and we will add 2 drops of phenolphthalein indicator. We'll mix the solution well, and then we have a burette here that is filled with 0.1 moles per decimeter cube concentrated HCl solution, and we will titrate this solution using the HCl solution we have in the burette. Now students, we are quite close to the end point. We can still see a pink color in the medium. However, with a few more drops, we will see this pink color disappear. At that point, we will take down our burette reading. Now students, we can very clearly see we have obtained our endpoint. Our pink color in the medium has now completely disappeared. So if you want to read the burette reading at this point, we will have to bring down our burette to our eye level, and then we can proceed to read the burette reading. And the reading is 5.2 milliliters. So first titration reading is going to be 5.2 milliliters. So to titrate the hydroxide ions present in the medium of this calcium hydroxide solution, we spend 5.2 milliliters of 0.1 moles per decimeter cube HCl solution. Now let's move on to our second titration. Now students, we move on to our second titration. So we have another 25 milliliter volume of the same solution. We will be adding a few drops of phenolphthalein, and then we'll mix the solution really well. And then we'll proceed to our titration. So our initial burette reading for this titration is 5.2. Then we will start to titrate little by little by gradually adding the HCl solution into the titration flask, and we'll be swirling the mixture or solution in the titration flask around as we add our HCl. And you will notice we have almost obtained a colorless solution. So at this point, we will add HCl a bit more carefully. Now we have obtained our endpoint. We cannot see any pink color in the medium. We cannot see any pink color in the medium. So we have obtained our endpoint. Now students, we have obtained our endpoint. Let's take a look at the final Bureau reading. Our final Bureau reading is above my eye level. So let's bring it down to my eye level. It is now at 10.3, right? So the final Bureau reading is 10.3. We started off at 5.2 and the final Bureau reading is 10.3. So the second titration reading is going to be 5.1. 5.1. So now let's move on to our third titration. Now we move on to our third titration. In this titration flask, we have a 25 milliliter volume of the same solution, and we will be adding 2 drops of phenolphthalein as we did in the previous 2 titrations. Then we will mix this solution really well, and then we can proceed to our titration by adding HCl into this titration flask with the use of this burette. So before we start adding HCl, we need to remember the initial burette reading. Initial burette reading is 10.3. Now let's add HCl drop by drop into our titration flask. Now we can see, students, we have a very faint pink color. With 1 or few more drops, we might obtain our endpoint. At this point, we have obtained our endpoint. So let's take a look at the burette reading now. So the burette reading is 15.6. Burette reading is 15.6. Initial reading was 10.3 and our final reading is 15.6. So the difference between the two is 5.3. The difference between the two is 5.3. So for the first titration, we obtained a reading of 5.2, second titration 5.1, and the third titration 5.3. So students, these are the readings we obtained when we titrated a saturated calcium hydroxide solution that we prepared by dissolving 1 gram of calcium hydroxide in 0.1 moles per decimeters cube concentrated nitric acid solution. So we prepared this saturated calcium hydroxide solution by dissolving 1 gram of calcium hydroxide in 0.1 moles per decimeters cube concentrated nitric acid solution. So in lower pHs, we are going to observe whether calcium hydroxide dissolves more. So this saturated calcium hydroxide solution was prepared by dissolving 1 gram of calcium hydroxide in 0.01 moles per decimeters cube concentrated nitric acid solution. So the pH of the solution before we dissolved calcium hydroxide in it was 2. pH of the solution was 2. So when we dissolved calcium hydroxide in a solution that has a pH of 2, we are going to observe whether it was more soluble or less soluble in such a solution by doing another titration. So students, after you do these titrations, we have to calculate how much of the calcium hydroxide out of the 1 gram of calcium hydroxide we added into these solutions have actually dissolved in these aqueous mediums. So we will be doing those when we move out of the lab and into our whiteboard to do the calculations. So now let's move on to our next solution, where we titrate a solution formed by dissolving 1 gram of calcium hydroxide in 0.01 moles per decimeter cube concentrated nitric acid solution. Now students, we move on to the next solution. So the next solution of calcium hydroxide was prepared, like I mentioned earlier, by dissolving 1 gram of calcium hydroxide in a 0.01 moles per decimeter cube concentrated nitric acid solution. So we have filtered this solution because what we are preparing is a saturated solution, and as you may know, saturated solutions can be identified by having some of the solid that we added undissolved in the bottom of the beaker. So just to remove that excess calcium hydroxide solid, we have filtered this. We have observed how the filtration process is done, and now we are going to be withdrawing 25 milliliters of this solution, saturated calcium hydroxide solution that we prepared by dissolving 1 gram of calcium hydroxide in 0.01 moles per decimeter cube concentrated sodium hydroxide solution into each of these titration flasks. So to remove 25 milliliter liquids of this solution and transfer it into the titration flask, we'll be using our pipette that we have over here. So using a pipette, we can withdraw 25 milliliters like this, and then after withdrawing 25 milliliters exactly, we can transfer that into a titration flask. Now students, after taking 25 milliliters into one titration flask, the same process will be repeated for the other 2 titration flasks as well. So we have 2 titration flasks here. To those titration flasks as well, we will measure 25 milliliters of this solution. Now we are transferring it into our second titration flask, and the same process will be repeated for the third titration flask as well. After that, students, we can move on to titrating this solution. To titrate this solution, we'll be using the same HCl solution we used earlier, and we'll be adding 2 drops of phenolphthalein indicator, and we will mix it really well. And afterwards, we will be titrating this solution using 0.1 moles per decimeter cube concentrated HCl that we have in this burette. So the burette is filled all the way to the top. Burette is filled all the way to the top. So initial burette reading is 0, and we are starting to add our HCl drop by drop into this medium while making sure that the solution is mixed well when we're adding HCl. We can see we are nearing the end point. You can see the color of the solution is decreasing gradually as we add HCl. Now students, we have a very light pink color. At this point, we are few drops of HCl away from obtaining our endpoint. So let's add a few more drops little by little until we observe a colorless solution. At this point, students, we have obtained our endpoint. We no longer observe a pink color in the medium. So therefore, we have now obtained our endpoints. So let's take a look at our burette reading. As you can see, the burette reading is above my eye level. So we will bring down the burette so that I can easily read the burette reading. So the burette reading is 8.8. Burette reading is 8.8 milliliters. So our first burette reading is 8.8 milliliters. So we can now move on to our second titration. Now we move on to the second titration. And we are going to be adding phenolphthalein as the indicator. And then we'll mix the solution really well. After that, we can proceed to the titration. Now keep in mind, students, again, the initial burette reading is going to be 8.8. So keeping that in mind, we will start our titration. Now students, we can see the color of the aqueous medium is decreasing. We are closing in on the endpoint. With just a few more drops, we will have our endpoint obtained. There's a slight pink coloration still, so we will add one more drop. The pink coloration still exists, so we will add another drop. We will continue adding HCl drop by drop until this pink color completely disappears. Now the solution is completely colorless. So since we have obtained our endpoint at this point, so our endpoint is 17.5. Now students, our endpoint is 17.5. So our initial Buret reading was 8.8. Our initial Buret reading was 8.8 and our final Buret reading is 17.5. So the titer value is going to be, or titer volume is going to be 8.7. So initial titer value was 8.8 and our second titration's titer value is going to be 8.7. So now our initial titer volume was 8.7. Second titration's titer volume is 8.7. So now students, we will be moving on to our third titration. Now we are going to move on to the third titration. We'll be adding our indicator first before we start the titration. We'll be adding 2 drops of phenolphthalein. We'll mix the solution well. And we'll proceed to titrate this solution. So students, the initial Buret reading is 17.5. After noting it down, we will be moving on to the titration. Now the pink color in the medium has slightly decreased. So we are nearing the end point now. You can see there's only a light pink color in the medium. There's still a very light pink color, so we add another drop to make sure we have obtained our endpoint. Even with the addition of another drop, the pink color remains, so we will add another drop. The pink color persists, so we will add a few more drops until we obtain a colorless solution. So students, by now we have obtained a colorless solution. A drop was able to change the solution from pink to colorless. So now we have obtained our endpoint. Let's take a look at the Buret reading. Now students, the Buret reading is 26.2. Buret reading is 26.2. So the initial reading was 17.5 and the final Buret reading is 26.2. Our difference between these two values will give our titer volume, or the amount of HCl we added to this titration flask. So for the third titration, our titer volume is going to be 8.7. 26.2 minus 17.5 is 8.7. So students, we have now seen the solubility of calcium hydroxide in different pH values. We have obtained our titration related data for all of these solutions that we have over here, except for this solution as we explained in the beginning of this experiment. Since all of the calcium hydroxide is completely dissolved there, we will not be able to carry out a titration with this solution. However, when it comes to the other two solutions, we have carried out our titration with the use of 0.1 moles per decimeter cube concentrated HCl solution. So we will have to move on to the lab and discuss which solution was capable of dissolving more calcium hydroxide with the use of the data we have collected here. So students, that part will come after you have completed all of the practical components that we have to complete in this experiment here. Afterwards, we will move out of the lab and we will carry out the calculations that are necessary to indicate which solution was able to dissolve more calcium hydroxide. So now let's move on to our next titration. Students, we move on to yet another saturated calcium hydroxide solution that we have prepared in a different way. So this time around, what we have done, as you saw in the initial bits of this experiment, is preparing a saturated calcium hydroxide solution by dissolving 1 gram of calcium hydroxide in 0.05 moles per decimeters cube concentrated sodium hydroxide solution, and then dissolving another 1 gram of calcium hydroxide in 0.025 moles per decimeters cube concentrated sodium hydroxide solution. So we have two different sodium hydroxide solutions here, and in each of those solutions we have dissolved 1 gram of calcium hydroxide. So calcium hydroxide equilibrium will be affected by a common ion that is present in this sodium hydroxide medium. When it comes to sodium hydroxide, it fully dissociates to release sodium 1 plus and hydroxide ions in the aqueous medium. So hydroxide ions in the aqueous medium will act as a common ion in the calcium hydroxide equilibrium. So students, we are going to observe the effect of common ion, which is hydroxide ion in this case, and how this hydroxide ions affect the calcium hydroxide equilibrium when it is dissolving in an aqueous medium. So now we will take our calcium hydroxide saturated solution that we prepared by dissolving calcium hydroxide in 0.025 moles per decimeters cube concentrated sodium hydroxide solution. So after we prepared the solution, you observed certain amount of calcium hydroxide remained undissolved at the bottom of the beaker. So we have now filtered that solution and we have taken it to a separate beaker here. And we will withdraw 25 milliliters of this solution using a pipette, and then we will transfer it into each of these titration flasks as we have done in the previous instances. So let's move on to do that. After measuring 25 milliliters with the use of our pipette, we can now transfer it into our first titration flask. We can do the same for the other two titration flasks as well. So we have two other titration flasks here. We will repeat the same process for these two titration flasks as well. We have taken 25 milliliters of the solution to the second titration flask. We'll do the same for the third titration flask as well. Now, students, we have measured 25 milliliters of the solution into each of these titration flasks. Keep in mind, these are saturated calcium hydroxide solutions. Now, these saturated calcium hydroxide solutions were prepared by dissolving calcium hydroxide in different other solutions like calcium chloride, sodium hydroxide, nitric acid, and we prepared a set of solutions by dissolving calcium hydroxide in distilled water at different temperatures as well. So this particular solution is prepared by dissolving calcium hydroxide in 0.025 moles per decimeter cube concentrated sodium hydroxide solution. So we are now going to add our indicator phenolphthalein. And students, we have now filled our burette all the way up to 0 line. This burette is filled with 0.1 moles per decimeter cube concentrated HCl solution. So using that solution, we are going to start titrating the solution in our titration flask. Now, students, you can see the color has started to go down, and we are going to add more HCl until we observe a clear solution or colorless solution. There's still a very light pink color. We'll have to add one additional drop. At this point, that very light pink color that was earlier observed in the medium can no longer be observed. So we have obtained our end point. So our end point is at a higher point than our eye level. So we will bring it down to our eye level. So our end point is at 9.5. Our end point is at 9.5. So our first titration volume was 9.5 milliliters. So while noting it down, we can now move on to the next titration. Now, students, let's move on to the second titration. We have another titration flask filled with 25 milliliters of the solution, and to that we can add 2 drops of phenolphthalein indicator. Then we can mix the solution well, and we can proceed to titrate this solution with our HCl solution we have in the burette. Before we start the titration, the initial burette reading is 9.5, so you should note it down before we start the titration. Initial burette reading is 9.5. We will start adding HCl slowly. You can see gradually the color that we observe in the solution over here decreases. The pink color will gradually become lighter, and when it is quite light in color, we will start to add HCl more slowly. You can see now there's a bit of a lighter color pink observed in the solution. We can proceed to add HCl drop by drop like this. And we will stop adding HCl when you observe a colorless solution. We have to add one more drop. Now the medium is colorless. So this is the end point for our second titration. Now let's take a look at the Bureau reading. Bureau reading is 18.9. Bureau reading is 18.9. So students, after taking a look at the final Bureau reading, we can subtract the initial Bureau reading. Initial Bureau reading was 9.5 and the final Bureau reading was 18.9. So the difference between the two would give us our second titer volume. For the second titration, the second titer volume is 9.4. So please note it down so that we can move on to our third titration. Now we move on to our third titration. We have our titration flask filled with 25 milliliters of a solution that we took for the previous two titrations as well. And we will proceed to add phenolphthalein, 2 drops of phenolphthalein into the titration flask. We'll mix it well. And then we can start our titration. Students, keep in mind when you are starting the titration, the initial reading is 18.9. We finished the second titration, or the final reading after the second titration was done was 18.9. So in the third titration, that will become our initial burette reading. After noting it down, we can move on to our third titration. So we will slowly add HCl dropwise until we see a lighter shade of pink. And then at that point, we will start to add HCl a bit slowly until we obtain a clear colorless solution. We have now obtained a very light pink color in the medium. So we can now add HCl very slowly until our solution is completely colorless. Now students, we have obtained our endpoint. So at this point, we can see the solution is completely clear. So therefore, we have obtained our endpoint. So it's now time to take a look at the Buret reading. So the final Buret reading is 28.2. The final Buret reading is 28.2. So students, after noting this 28.2 final Buret reading, we can proceed to calculate the third titration's titer volume. So the initial Buret reading was 18.9 and the final Buret reading is 28.2. When you subtract the initial Buret reading from the final Buret reading, we get to a titer volume of 9.3. So the titer volume here is 9.3. So for the first titration, the reading that we got was 9.5. Second titration, it was 9.4. And the third titration, it was 9.3. So we will note this down and we will be moving on to the next solution. And now students, we are going to be moving on to the next solution. The next solution that we are going to talk about was formed by dissolving 1 gram of calcium hydroxide in 0.05 moles per decimeter cube concentrated sodium hydroxide solution. And we could tell that this was also a saturated calcium hydroxide solution, as we had a lot of calcium hydroxide remaining at the bottom of the beaker, which was not able to dissolve in this medium. After we allowed it to obtain an equilibrium, we filtered the solution to remove the solid that was collected at the bottom of the beaker. And what we have over here is our filtered calcium hydroxide solution that we prepared by dissolving calcium hydroxide in 0.05 moles per decimeter cube concentrated sodium hydroxide solution. And now, using this clean pipette, we can withdraw 25 milliliters of this solution into our titration flask. And then after that, we'll repeat the same process for the next 2 titration flasks as well. We have transferred 25 milliliters of the solution into 1 titration flask, and we can repeat the same for the next 2 titration flasks like this. And now finally we'll be filling up this pipette one more time to transfer 25 milliliters of the solution into our third titration flask. Now students, we are going to move on to the titration after adding the indicator into these titration flasks. So we have our burette here, again it is filled with 0.1 moles per decimeter cube concentrated HCl solution all the way to the top. And after adding our phenolphthalein indicator to our first titration flask, we can move on to titrating this solution with the use of 0.1 moles per decimeter cube concentrated HCl solution. So now we can start the titration. And whenever you start the titration, you should note whether the initial burette reading is 0 or whether it's a different value. So at this point, since we have just filled this burette, the initial burette reading is exactly at 0. Now, as you can see, we are slowly adding HCl into this medium, and when you're adding HCl, always make sure to mix the solution in the titration flask really well so that we can observe if there's any color change very clearly. Now students, we have over here a very light pink color. So when you add a little bit of HCl, you will see this pink color will become even lighter. So we are close to obtaining our endpoint. With just one more drop, we might obtain our endpoint. Yes. So we have now obtained our endpoint, and the final burette reading is 13.9. Final burette reading is 13.9. So that is the first titration's titer volume. So now we are moving on to the second titration. Now students, we move on to the second titration. So we have another titration flask filled with 25 milliliters of our solution. We have our phenolphthalein indicator, and we will be adding 2 drops of this phenolphthalein indicator into our titration flask, as we have done in many of the previous instances. And then you can see, since this medium is alkaline, the solution turns pink, and we'll be titrating this against HCl solution. So after the first titration was over, our final reading in the first titration was 13.9. So our initial burette reading for the second titration is 13.9. Then we can start our titration. Now students, as you can observe here, the color of the solution has gone down. So we can carefully add a few more drops of HCl, and we will obtain our endpoint after the addition of few more drops of HCl. there is still a little bit of a pink color present in the medium. We will swirl it around to see if the pink color disappears, because we have added one additional drop now. So there's no longer a pink color visible here. This indicates that we have reached our endpoint. So at the endpoint, let's take a look at the buried reading. Buried reading is 27.7. Buried reading is 27.7. So this is our final reading. Initial reading was 13.9. So subtracting 13.9 from 27.7, we get our second tighter volume, which is 13.8. So our second tighter volume is 13.8. First one was 13.9. So let's move on to our third titration. So we have our third sample here. So there's a 25 milliliter volume of our solution here in this titration flask. We have our phenolphthalein here, and we will be adding 2 drops of our phenolphthalein into this titration flask. We will mix it well, and then we can proceed to start our titration. And as I mentioned earlier also, whenever you're starting the titration, take a note of the initial butyrate reading. So the initial butyrate reading here is 27.7, and after noting it down, we can start our titration. Now students, we are very close to obtaining our endpoint. You can see the pink color is very faint here. The pink color still persists in the medium, but now it has completely turned colorless. It has completely turned colorless. So this is our endpoint. So let's take a look at the endpoint here, students. So the butyrate reading is somewhere down here. So since it is somewhat difficult for us to read the butyrate reading when it is covered by the butyrate holder, we can bring the butyrate down a bit further, and then we can read the butyrate reading after we bring it down a little bit. So the butyrate reading at this point is 41.5. The butyrate reading is 41.5. The initial butyrate reading was 27.7. The final butyrate reading is 41.5. The difference between the two is 13.8. So the final titration that we did for this solution also resulted in a tighter volume of 13.8. So now students, after noting down all of the 3 tighter volumes or readings for all 3 titrations, now students, after noting down all of the readings we obtained from this set of titration and the set of titrations we did for the previous solution, we can carry out calculations to determine in which sodium hydroxide solution calcium hydroxide dissolved more. And you would come to realize, when you have a common ion in the medium, dissolving calcium hydroxide becomes more difficult, especially when the common ion concentration increases. Dissolving calcium hydroxide in the medium would be more difficult. Solubility of calcium hydroxide will drop when the common ion concentration increases. Now students, after noting this, we can now move on to the next solution. Now students, we are going to be looking at the solubility of calcium hydroxide in distilled water. Not only distilled water at room temperature, but we will be observing the solubility of calcium hydroxide in distilled water at 25 degrees Celsius, also known as the room temperature. And then we have distilled water at 50 degrees Celsius and distilled water at 90 degrees Celsius. And we are going to observe the solubility of calcium hydroxide in distilled water at each of these different temperatures. So over here students, in the beginning of our experiment, we dissolved calcium hydroxide in water that was at room temperature. So since it was a saturated solution, we had some solid calcium hydroxide remaining in the medium. We allowed the medium to obtain an equilibrium, and afterwards we have filtered out the solution to separate out calcium hydroxide aqueous saturated solution. So what we have in this beaker is our calcium hydroxide saturated solution that was obtained by dissolving calcium hydroxide in distilled water at room temperature. So now students, we are going to withdraw 25 milliliters of this solution into this titration flask. We can do so by using a pipette. Using this pipette, we can withdraw exactly 25 milliliters of this solution. Afterwards, we can transfer it into this titration flask. And then we can repeat the same process for the other two titration flasks as well. We have two more titration flasks here, and we can repeat the same process for these two titration flasks as well. So let's go ahead and do that. Now students, we have measured 25 milliliters of a saturated calcium hydroxide solution into 3 titration flasks. So now it is time for us to move on to titration. So titration will be carried out by adding HCl with a concentration of 0.1 moles per decimeters cube. So we have HCl filled all the way up to the 0 point over here in our burette. And we will be titrating this solution in our titration flask, which is a alkaline solution because we have dissolved calcium hydroxide in it. So therefore we can use phenolphthalein as an indicator. Since the medium is alkaline, you will observe the solution turns a pink color. So we will mix the solution well after adding phenolphthalein indicator, and then we will be titrating this against 0.1 moles per decimeter cube concentrated HCl solution. Let's add HCl little by little to this medium. Make sure as you add HCl into the medium to mix the solution really well. At this point, students, you can see the color of the solution is a very light pink. So this is a very light pink color that you observe over here. This indicates we are close to the end point, so we can add HCl slowly until we observe a clear, colorless solution. So with that last drop, we can observe that the solution is now clear. So at this point, we will be able to take our burette reading. Our burette reading is above our eye level, or the meniscus over here is above our eye level. We can read down to our eye level and we can observe the burette reading with the use of a white background. And the burette reading as it stands is exactly 10 cubic centimeters. So for the first titration we carried out, the burette reading is 10 cubic centimeters, or we can say the titer volume is 10 milliliters. So first titration reading is 10 milliliters. Now we can move on to the next titration. Now students, we are moving on to our second titration. So we have another titration flask filled with the same solution. We have our phenolphthalein. We will add 2 drops of our phenolphthalein into the titration flask like so, and then we will mix it really well. And then we can start the titration. And before starting the titration, we have to observe our initial burette reading. Initial burette reading is 10. Initial burette reading is 10. So after noting it down, we can move on to our titration. Now students, you can see we have obtained a bit of a lighter pink color. So from this point onwards, we can start to add HCl very slowly, and we can see we have now obtained our endpoint because the solution is no longer pink in color. So at that point, we can read our burette reading. Our burette reading is 20.2. Our burette reading is 20.2. Our initial burette reading was 10. Final burette reading is 20.2. The difference between the two volumes will give you the volume of HCl we have added to this titration flask to obtain our endpoint. So the difference between 20.2 and 10.0 is 10.2. So the second titer volume is 10.2 milliliters. So now let's move on to our third titration. Now students, we are moving on to the third titration. We have another 25 milliliter volume of the same solution as well as phenolphthalein. So let's add 2 drops of phenolphthalein into this calcium hydroxide saturated solution, and let's mix the solution really well. Afterwards, we can proceed to our titration. So before we begin the titration, we should note down the initial burette reading. The initial burette reading is at 20.2. So after noticing this, we can move on to our titration. Now students, we have obtained a bit of a lighter pink color. There's still a very slight pink color in the medium, so we'll add just one more drop. At this point, students, we have obtained our endpoint. Let's take a look at the burette reading. The burette reading is 30.3. The burette reading is 30.3. The initial reading was 20.2. The final reading is 30.3. The difference between the two readings is 10.1. So the third titration gave us a titer volume of 10.1. In the initial titration, the titer volume was 10.0. Second titration, the titer volume was 10.2. And the third titration, the titer volume was 10.1. So after noting these titer volumes down, we can now move on to the next solution. Now students, we move on to another solution, and this solution was made by dissolving calcium hydroxide in distilled water that was at 50 degrees Celsius. And we allowed the equilibrium to be established at the same temperature. And after the equilibrium was fully established, we have filtered the solution to remove any solid particles coming into the titration flask when we are withdrawing 25 milliliters of the solution and transferring it into our titration flask. So over here is the filtered solution of calcium hydroxide that we prepared. And now with the use of our pipette, we are going to transfer 25 milliliters of this solution into our titration flask. When handling hot solutions like this, you have to be careful not to burn yourself, especially when you are conducting any experiment revolving around heating. Take proper precautions. After transferring this solution, we will leave it aside, and we will do the same to the other two titration flasks as well. We have maintained a temperature of 50 degrees Celsius when we prepared the solution until now. So after preparing the solution until now, the temperature was maintained. Now we move on to the third titration flask. So we will withdraw another 25 milliliter liquid of this solution into the third titration flask. Now students, we are going to add our phenolphthalein indicator as we have done in the previous experiment. We'll add 2 drops of phenolphthalein indicator. Then we will mix the solution. And then we will move on to titrating the solution using our 0.1 moles per decimeter cube concentrated HCl solution. So we have filled this burette all the way to the top with that solution. Now Since we know the Bureau reading, initial Bureau reading is 0, we can straight away start to titrate our first 25 milliliter sample of the solution we have over here. Now students, we will be gradually adding HCl into the medium. You can see the color changing gradually, and there's still a little bit of pink color in the medium. So with a few more drops, this color will completely change into a clear solution. So when you are sometimes having a little bit of warm water or aqueous medium in the medium, you might see a small amount of water vapor will fog up the inner walls of the titration flask. So this might sometimes not show you a clear color change. So be mindful when you're doing titration. Don't miss out on the end point just because it is sometimes not very clear when you have hot liquid in the titration flask. So hence the color that you see over here is still a little pink. So now let's add a little bit more HCl, and you will observe that the solution turns completely colorless. So solution turned completely colorless at this point. So this is our first titration, and now let's move on to obtaining our reading for the first titration. The reading for the first titration is 9.8. Reading for the first titration is 9.8 cubic centimeters. Now we'll be moving on to our second titration. Now students, let's move on to the second titration. So we have another 25 milliliter volume of the same solution over here, and we will add 2 drops of phenolphthalein into this aqueous medium, and after mixing it, we can proceed to our titration. Now keep in mind students, the previous titration gave us an endpoint at 9.8. So the initial Bureau reading when you're doing the second titration is 9.8. So after noting the initial Bureau reading, we can start adding HCl. Now students, we can see we have come very close to the endpoint because we observe a small pink color still in the medium. So we have to add a few more drops of HCl, and just a single drop actually was able to change the color from pink to colorless in this case. So we have obtained our endpoint here students. Now let's take a look at the final Bureau reading. The final Bureau reading is 19.5. The final Bureau reading is 19.5. Now let's move on to calculating the actual titer volume for this second titration. So the initial reading was 9.8 and the final Bureau reading was 19.5. So the difference between the two is 9.7. So for the second titration, the titer volume is 9.7. So now let's move on to our third titration. Now students, we are moving on to the third titration here. So we have our third 25 milliliter sample of the solution here, and we have this phenolphthalein, and we will be adding 2 drops of phenolphthalein into our titration flask. After mixing it really well, we can start our titration, and as I mentioned earlier, we have to take a look at the initial Bury reading. Initial Bury reading is 19.5. After noticing the initial Bury reading, we can start the titration. Since we know around which point we are obtaining the endpoint, I have added HCl a little bit faster this time around. So we have now a very light pink color in the medium. That means we are close to the endpoint. We will add a few more drops, maybe just 1 more drop, and let's observe whether we obtain a clear solution. Solution is still a little pink in color. We'll add another drop. At this point, students, we have now obtained a clear solution or colorless solution. So let's take a look at the Bury reading at this point. The Bury reading at this point is 29.2. The Bury reading is 29.2. The initial reading was 19.5 and the final Bury reading was 29.2. And the difference between the two is 9.7. So for the third reaction, the titer volume is 9.7. For the first titration, the volume of HCl that was spent was 9.8, and for the second and the third titrations, the volumes of HCl that was spent to obtain the endpoint was 9.7 cubic centimeters of HCl. So after noticing this, you would have observed when it comes to titrating the calcium hydroxide at room temperature or saturated calcium hydroxide solution at room temperature, we spend more HCl to titrate that solution. And now we have calcium hydroxide solution that was dissolved at a higher temperature in water. However, at that point, the amount of OH minus ions in the medium is seemingly less than the OH minus ions that came into the medium when we dissolve calcium hydroxide in distilled water. So we observe as we increase the temperature when it comes to our calcium hydroxide solutions, solubility has started to come down. So we'll move on to talking about further details about calcium hydroxide when we move out of the lab into our classroom and discuss the theory revolving around calcium hydroxide. So after we are done with the third titration here, we are now moving on to another saturated calcium hydroxide solution. Now students, we are going to move on to another saturated calcium hydroxide solution, and this solution is made by dissolving 1 gram of calcium hydroxide in distilled water at 90 degrees Celsius. So as we initially dissolved this in 90 degrees Celsius water, we saw some calcium hydroxide did not dissolve. So we moved ahead and we filtered it out. So what we have over here is the filtered calcium hydroxide saturated solution, and it is at 90 degrees Celsius. After making the solution, we maintain the temperature at 90 degrees Celsius up until this point. So let's remove 25 milliliters of this solution into these 3 titration flasks that we have over here. So we can use our pipette and we can draw 25 milliliters. of this solution into our pipette. Then we can transfer these 25 milliliters of our solution into titration flasks. We can proceed to do the same to the other two titration flasks as well. We have now filled 25 milliliter volumes of our calcium hydroxide solution. We have now filled 25 milliliter volumes of calcium hydroxide into two titration flasks. Now this is our final titration flask. Now we are transferring the final volume of we are transferring the final 25 milliliter volume of calcium hydroxide into the third titration flask. And after doing so, we can leave the pipette aside and we can move on to our titration. So as done in the previous instances, we have our HCl filled into the burette all the way up to the 0 line, and we have our calcium hydroxide samples over here, and we have phenolphthalein. So since this is an alkaline solution, we'll be using phenolphthalein indicator. We'll add 2 drops of phenolphthalein indicator, and then we can proceed to titrate this solution with the use of 0.1 moles per decimeter cube concentrated HCl solution. We can gradually start to add HCl little by little, and when we observe a light pink color, we can add HCl very slowly to obtain a more accurate endpoint. Now students, we have come to observe a very light shade of pink. So with a few more drops of HCl, this pink color will turn colorless. We have to add another drop. So with the last drop that we added, we have now turned the solution entirely colorless. After bringing down the burette to our eye level, we can observe the burette reading. So the burette reading as it stands is 9.0. 9.0 is the burette reading for our first titration. So students, for the first titration, we spent 9 milliliters of our HCl solution to obtain an endpoint. So now let's move on to our second titration. We have taken our second 25 milliliter volume of a calcium hydroxide solution, and we have just added our phenolphthalein. Now let's titrate this solution with our HCl solution we have over here. We'll gradually start to add HCl. Now we have obtained a very pale pink color. Let's add a few more drops to obtain a colorless solution. There's still a very slight pink color which the camera might not be able to pick up, so to remove that very slight pink coloration in the medium, we will add another drop of HCl. Now the solution is entirely colorless. So now let's observe our burette reading. So the initial reading was exactly 9.0. Now let's move on to the final burette reading. So the burette reading is 17.8. The burette reading is 17.8. Now students, the initial burette reading was 9.0 and the final burette reading for the second titration was 17.8, and the difference between the two is 8.8. So 8.8 is our second titer volume. Now let's move on to our third titration. Now we are moving on to our third titration. We have 25 milliliters of the same solution over here, and we will be adding 2 drops of phenolphthalein into the solution, and then we'll mix it really well. Afterwards, we can move on to our titration. Dear students, we need to notice the initial burette reading. Initial burette reading is 17.8. Initial burette reading is 17.8 for the third titration. So after noticing that, we can proceed to add HCl little by little. Now we have obtained the endpoint for the final titration, and let's take a look at our burette reading at this point. Let's move on to observing a burette reading. The burette reading is 26.8. Burette reading is 26.8. Initial burette reading was 17.8 and the final burette reading is 26.8. The difference between the two is 9.0. So the third titration resulted in a titer volume of 9.0 milliliters. Now students, for the 3 titrations that we conducted, the titer volumes were 9.0, then we observed a titer volume of 8.8, and then again a 9.0. Now students, in summary, in this experiment, we wanted to observe the solubility of calcium hydroxide in different mediums, and we wanted to calculate the KSP, solubility product of calcium hydroxide. And to determine the solubility of calcium hydroxide in different aqueous mediums, we dissolved calcium hydroxide in nitric acid solutions, sodium hydroxide solutions. Apart from that, to observe the solubility of calcium hydroxide in different mediums, we dissolved calcium hydroxide in different aqueous media. And we wanted to observe if the solubility of calcium hydroxide varied when the pH of the aqueous medium was changed, when the temperature of the aqueous medium was changed, and when there were common ions present in the aqueous medium, how the calcium hydroxide solubility varied. So we observed when there were common ions present in the medium, calcium hydroxide solubility decreased. And if the common ion concentration was high, calcium hydroxide became less soluble in that medium. When it comes to talking about pH, when the pH of a medium is lowered, you have higher concentration of H+. In such mediums, we observe that calcium hydroxide becomes more soluble. And finally, we increased the temperature of the aqueous medium that we used to dissolve calcium hydroxide. And we observed as we increased the temperature of the water that we used to dissolve calcium hydroxide solubility decreased. So when we increase the temperature of the medium, calcium hydroxide solubility decreases, meaning calcium hydroxide equilibrium shifts to the left when we increase the temperature of the medium. So we have noticed these observations, and now it is time for us to take our titration related data that we have gathered into our classroom and then discuss the findings that revolve around these titrations. So students, let's move on out of the lab and calculate the KSP value of calcium hydroxide and observe through calculations how the solubility of calcium hydroxide varied when we dissolve calcium hydroxide in different aqueous solutions.